Hello. Hello, good morning, everybody. Thank you for, can you hear me?
Yes.
Thank you for the introduction. My work is a collaboration between the NanoLab group of the University of Salamanca and the Departamento de Físicas de Materiali of the Universitat Complutense of Madrid. Basically, this is the outline of my talk. I will start at the beginning with the motivation. In particular, I will present you some recent work on graphene nanoconstriction. And after that, I will start to talk about my work. In particular, I started to fabricate and characterize graphene on silicon oxide with the chemical treatment. And after that, I started to work also with graphene nanoconstriction encapsulated graphene, in which I defined the constriction with the UCreation method applied for the first time to encapsulated graphene. And at the end, I conclude and I present you some possible future work. Okay, the quantization of the conductance into the material, in particular into the standard heterostructure, is something very well known. In particular, since a lot of years, one of the first jobs is this work of Van Vis, in which he observed quantized conductance in a system of heterostructure of gallium arsenide and aluminum gallium arsenide, in which he confined the electron thanks to the bidimensional gas thanks to the external gates. And the system is particularly characterized by very high mobility at very low temperature. So we needed, for quantization of the conductance, a bidimensional gas, basically, and a mobility very, very high, and the confinement of the charge, of course. So graphene is a natural bidimensional material, so it's fantastic for this to study quantization of the conductance, and it presents very high mobility, especially when is in the form in which it is encapsulated in hexagonal boron nitride. And typically, there are two different ways in which people obtain the quantization of the conductance in graphene without the application of magnetic field. The first, here I present you two recent work in which in single layer graphene and bilayer graphene were applied electrostatic potential gates. So as you can see, we can observe the quantization of the conductance. This is similar to the work, to the idea of Condensed. The other way is to physically etch the nanoconstriction, so to obtain really a physical constriction. On this, in reality, people started since a lot of years, from the beginning of this discovery of graphene, to define the graphene in nanoribbon, nanoconstriction, but at the beginning the mobility was too low and other effects typically appeared. Probably one of the first work in which conductance of the quantization appeared was this work of Nico Trompos, in which he studied suspended graphene. So with the suspended graphene is achieved easily basically ballistic regime because the suspended graphene has very high mobility. But the main limitation is that the possibility to define the constriction with a particular design. This in particular was were fabricated with a technique called current annealing. More recently, Terres studied different constriction in encapsulated graphene, so he easily achieved very high mobility and ballistic regime, and he studied different constriction with encapsulated graphene with different slides, observing quantization in form of spike. Studying the transport property of the constriction with the semi-classical formula, so the conductance respect the width of the channel and the wave number multiplied for the transmission factor, the transmission factor that he obtained was not so high, and the main reason was the high roughness of the constriction itself. Caridad overcome this problem because he obtained in graphene nanoconstriction very high, very low roughness constriction, typically of 1 nanometer. But he studied graphene on silicon oxide with a chemical treatment. So again, the ballistic regime is not is true only on few hundreds of nanometers, and the system was not so stable. When I started to work with graphene nanoconstriction, I started with graphene with hexamethylsilazane treatment. Thanks to this chemical treatment, the standard, the normal graphene on silicon oxide improved a lot the quality. This can be seen from the Raman spectra, in particular from the ratio between the 2T peak and G peak, improved a lot respect the standard graphene on silicon oxide. And the mobility that normally is possible to obtain are quite higher, typically more than 10,000 centimeters square on volt per centimeter. So this is a good compromise. Why? Because in graphene on silicon oxide is quite easy to define the constriction and also with good definition. For example, in this case, I defined a constriction of 85 nanometer. And from the measurement, from plotting the conductance respect the gate voltage, I observed some kind of quantization, and even if it's not exactly at the conductance quantum. The main limitation of this system of graphene on silicon oxide with this chemical treatment is the mobility is still low mobility graphene, and the system is not stable. Typically, the chemical treatment disappears after a few days in vacuum and low temperature. But in Salamanca, we are able to study graphene in encapsulated graphene devices. So we have our transfer system, and we are able to encapsulate graphene. Particularly for this work, I used a PPC method and polypropylene carbonate method. Basically, the idea is this one. At the beginning, we exfoliate a flake of HBN and a flake of monolayer graphene, and I pick up the HBN, put on the graphene, and after that, I pick up both and put on the bottom HBN, obtaining the final heterostructure. And the improvement of the quality of the encapsulated graphene is clear since from the Raman spectrum. We realize that if you applicate it in reality in different kinds of devices, particularly with Holberg geometry, we can estimate quite well the mobility that it is also very high at also at room temperature, typically more than 10,000 centimeters square on volts per centimeter. So the ballistic regime, we can say that is easily achieved in a length of 1 micron, more or less. And the indication of the high quality of our devices is also proved by the observation of the fraction quantum Hall effect at very low temperature and high magnetic field. So now we know how to fabricate the graphene in encapsulated graphene in devices in encapsulated graphene. Now we have to define the constriction. So at the beginning, we have two different ideas. One was we started a collaboration with the Carl Zeiss Center in USA, and the definition, the last step, so the definition of the constriction was made with this quite new system, Orion nanofab helium. With the use of helium, the resolution of the system is really impressive, and it's possible to define a very small constriction with very high quality in the definition. But unfortunately, I have to say we did only a few devices. The devices after the last step diet. So another possibility that we have here in Salamanca is to use our system, the ICP with the clear chip option. So basically, a dry chip process at very low temperature. And so we started to fabricate the first devices. And from the beginning, we saw that the constriction defined at very low temperature was better than the constriction defined at room temperature. In particular, this is very clear from the SEM image. Qualitatively, it's possible to see the definition in the two cases. But and there are more the higher rawness in case of room temperature. And when we carried some AFM measurements, we estimate also the rawness, and in particular, we found a rawness quite low, typically lower than 2 nanometers. So this is a very good result if you consider that we're talking about encapsulated graphene, where to etch the HPN is not so easy. It's not so easy. So we fabricate different devices. For example, this is one typical device. In this tilted image, you can see again the quite good definition of the constriction, and you can see that we use this for probe configuration. So we carried some 4 probe measurements. Basically, we inject the current in the external contact, and we measure the voltage in the internal one. So we obtain directly the resistance, and from the resistance, we obtain directly the conductance in respect of applying backgate voltage. When we compare the constriction with the semi-classical formula, so we plot the conductance respect, again, the wave number multiplied for the width of a channel and the transmission coefficient, we saw in this case of for a constriction of 200 nanometer, we saw that there is a linear behavior that is an indication of ballistic regime typically, and from the fit of this linear behavior, we observe a very high transmission coefficient. Very close to 1, so very close to the ideal one. And we obtain these results for different kinds of constriction. And in particular, more important, from the, if we zoom in the central part of the graph in particular, we can see a clear appearance of plateau. And these plateaus are clear if we plot also in the bottom the test conductance. From the minimum of the test conductance appear the corresponding plateau. And the sequence is very nice, and the separation is exactly the conductance 1, 2. We study also the behavior of the nanoconstriction respect at different temperatures. So we observe a dependence of the temperature, and in particular, the plateau or the minimum of the test conductance disappear with the temperature. We found that after more or less 15 Kelvin, the plateau starts to disappear completely. And this work, we worked every time with single layer graphene, but this work was also obtained with bilayer graphene. In fact, in this work, for example, they found more or less the same critical temperature.
So you have 2 minutes? Okay,
yes, thank you. Just to conclude, so we improved a lot the graphene nanoconstriction definition in encapsulated graphene, thanks to a new clear chip method applied for the first time to graphene. And we obtained basically higher values of the transmission coefficient comparing the behavior of the nanoconstriction with the semi-classical formula. We found a very good rawness, lower than 2 nanometers, and we observed an evidence of the conductance condensation for a very small structure. For the future, we want to study different kinds of geometry, not only nanoconstriction, but also nanoribbon, for example. We want to study nanoconstriction with graphite backgate in which we expect to reduce the carrier density, residual carrier density, and we want to use nanoposition for interest detection also. Okay, these are the two papers related to this talk. Thank you very much for your attention.
Thank you. Thanks. It's very interesting. So just to remind people, you can use the chat, raise your hands. Is there, just check if someone raised hands, no? Yeah, I will start then with the questions. I was wondering this technique, this cryogenic technique. So you said, well, I understood that it's very difficult. I mean, the bone nitride, it's very tough to, and so you show the results at 2 different temperatures, but in principle, is there, how does it change, let's say, or what's the, I guess you try different set of temperatures, or you try these 2, or how?
Exactly, no, I try different kind of temperature, and when in particular at low temperature, I noticed from the beginning, just comparing the SEM image, that the roundness of the constriction was much better. This was made at the beginning qualitatively just by SEM image, but after that we added also AFM measurements, so to quantitatively estimate the roundness.
Yeah. Yeah, I also was wondering, because you did mention also the technique, what was it, the helium microscope?
This is
so compared to that, is it better, the cryogenic one? Because you said that something like the devices were not surviving, or?
Exactly. The resolution it was, to be honest, because for the QH, in any case, we use EBL, electron beam process. So the resolution of EBL is lower of the helium nanofab resolution. But in any case, the results are very good. We want also to continue to continue the collaboration with ZEISS, but it's quite complicated. Also, for the graphene is quite also delicate, so it's also for the travel it's not easy to carry sometimes the device. And we don't know exactly what happened, but we did fabricate only a few samples, as I say, and at the end, we don't know exactly what is the reason. Probably the technique also is more invasive, probably, or more damage, probably, in some sense, the graphene. We don't know.
Yeah, okay, interesting. No one? I will continue then. So the other question is, because all the results you show of the quantization first, so if you maybe show the last ones, or so the plateaus, they are very short, right? I didn't get here. So this you can transform this basically in the gate voltage, right?
Yeah, exactly.
Horizontal axis. So is there a way to, you see, either to expand these plateaus or to have them also, and the other thing would be also, of course, to have them at higher temperature, but I understand the quality of your graphene is kind of like, you're at the top, let's say, of by encapsulating and doing exfoliation. So I don't see if from the quality of the material you can improve any of these parameters.
I think should be. Should be with the quality of, I think, but it's also with the improving more the edge definition. Yeah, exactly. I think it's possible to improve. Also, I don't know, probably to try, because now I think the bigger limitation is the EBL. So EBL process is probably using, I use it, for example, PMMA, but probably if I use a higher resolution resist, probably it's possible to improve more the edge definition than the constriction. Because I think that the quality of the graphene is quite high.
Yeah. Yeah, that's why what you showed from your before making the constriction, I guess, I don't know. You can
probably
much faster. Maybe it's suspended graphene, but yeah. All right. Okay, I don't see any questions. That's your last chance. If not, then thanks again, Vito.
Thank you.
Yeah. We move to the next talk. Is Amador Garcia Fuentes. You can share your screen.
Okay.
Sorry. Okay. It's coming now. Yeah. Yeah.
Now it's there. Yeah. You.
Thank you. Thanks. Go ahead.
Let me check. Oops, I don't know. Okay, so yeah, I start. Okay, so good morning, everyone. Welcome to this presentation, where I'm going to talk about some recent work that we have done, and Jaime Ferrer and myself at the University of Oviedo. And to be fair, I'm also going to talk about the work done by all these other people, these experimental colleagues, mainly at Delft. So the work that we did in Oviedo was to give a theoretical background to a few experiments performed by our experimental colleagues at Delft in the group of Gerre van der Sand. And in these experiments, they looked at the electronic properties of devices based on mechanically controlled break junction. And in one of these devices, they found quantum dot physics with an interesting behavior. So in this talk, I will show this behavior, and then I will give the explanation that we found for it. So, okay, so the main objective of this talk is to explain this interesting quantum dot physics that, as I will show, appear in some experiments where high tunability of the connections to the leads is achieved of several orders of magnitude. For this purpose, I will talk first briefly about previous work on graphene break junctions that will help us put into context the new experiments and the new results. Then I will show the details of the experimental device and the experimental results of this new experiment where quantum dot physics appear. After that, I will talk about a qualitative explanation to this peculiar behavior found in the experiments. And finally, based on theoretical simulations with type binding methods, I will put some numbers, and the qualitative explanation will hopefully become a quantitative one. Okay, so first I will talk about this previous work that was published here a couple of years ago. In this work, our colleagues at Delft prepared the following experimental graphene break junction device that mainly goes as follows. They transfer a graphene layer onto a flexible metal substrate coated with some kind of insulating coating. And then they define lithographically this bow tie shape in graphene and connect it to gold electrodes to be able to measure the current through the junction. And finally, as the substrate is flexible, they can bend the system, and the bending and unbending should open and close a gap in the middle of the bow tie. So then they measure the conductance of the device upon the opening and the closing cycle, and they do this at room temperature and in open air, and they find these oscillations in the conductance. And this oscillatory behavior is stable upon cycling, and here I show a map where they do 1000 cycles, and we see that the peaks always appear and always appear at the same position and with the same period. And this period, this distance here, is a little bit lower than 1 nanometer, but it is clearly larger than the lattice constant of graphene. So there's graphene. From the theoretical point of view, we are able to reproduce these oscillations with DFT or tie binding methods if we allow the graphene edges to slide one over the other, to overlap. So first, what we find is small oscillations, like this one, that are due to the periodicity of the structure. Then we have larger oscillations, like this one, that are due to quantum interference effects for electrons in a similar way to what happens with light inside a Fabry-Perot interferometer, where here the walls of the interferometer are the edges of the overlapping region. And finally, the largest oscillations with the period similar to that obtained in experiments are due to the combination of both effects. So for the purpose of our new work, we have to keep in mind that when we close the gap in the break junction, the graphene layers overlap one over the other, and that this leads to oscillations in the conductance due to quantum interference effects. Okay, so now let's talk about the work that concerns us now. In this new work, our experimental colleagues at Delft made this break junction device where that is similar to that shown before, but now they add graphite here and HBM to be able to apply a gate voltage. So now the transport properties of the device as it bends can be analyzed with respect to both the bias voltage and the gate voltage applied in the central region of the break junction. So then they look at the effect of the gate voltage for a given bending of the device, that is for a fixed position of the graphene electrodes. And here I show the differential conductance as a function of the gate voltage, and we can see or we find this all these well-defined peaks. Also, below we show the full current stability diagram, where we can see very well-defined Coulomb diamonds. All of these characteristic of Coulomb blockading quantum dots in both the Hall regime and the electron regime, and also although with diamonds with some irregular shapes in the surrounding of the charge neutrality point. So then it looks like somehow there is a quantum dot in our device. So we can compare our device to a quantum dot model as this shown here, where we have the source and the drain that are just the left and right electrodes, but we also have a central region, some kind of island, that is separated from the leads via contact resistances, and these contact resistances present also a capacitance. This central region is then the one that is affected by the gate voltage, via another capacitance. Just to remember, the idea below Coulomb blockade in quantum dots is that the levels of the island are weakly coupled to the electrodes, so electronic transport through the levels of the island can only happen when the levels are inside the energy window defined by the bias voltage between the source and the drain. As all the levels of the island can be shifted up or down with the gate voltage, the bias voltage that you need to get current through the system changes with the gate voltage, leading to these diamond shapes in the conductance. From the shape of these diamonds, we can obtain the capacitances of our model. And another thing is that the separation between the levels is the addition energy that each new electron needs to enter the island. And this addition energy has two main contributions, or two contributions. First, the single particle energy, that is mainly due to quantum confinement, and that for a chaotic cavity, like a quantum dot of irregular shape, follows a random distribution. And second, a U-term, that is due to the electrostatic repulsion between each new electron and the electrons already present in the island, that is roughly constant. And we saw here, for a given bending position, all the measured addition energies. And using some kind of Gaussian distribution like this one, we can estimate U to be of around 8 milli-electron volts, and the single particle energies to be mostly below 1 milli-electron volt. And from the value of U and the characteristics of the device, we can estimate the size of the island to be of around 60 nanometers. Okay, now we look at what happens when we change the bending position, when we close the gap. And what we see is that looking at a particular Coulomb diamond, we see that the shape of the diamond changes. This means that the capacitances of the dot are changing. And looking at the differential conductance, we see that the height and the width of the resonances is changing, and this means that the resistance, the contact resistances, or more precisely the gammas that represent the electronic coupling between the levels of the island and the electrodes are also changing as we close the gap. So then from the shape of one diamond, we can extract values of the different capacitances as we close the gap. And what we find is that while the gate capacitance and the source capacitance remain quite constant upon bending, the drain capacitance increases linearly as the gap is closed. Then, just from the experimental point of view, we have a quantum dot in our system for which the drain capacitance can be tuned mechanically. Okay, so our device has this behavior, but what is actually happening inside our device? Well, what do these measurements tell us? What are they telling us? The capacitance, roughly speaking, is a measurement of the connection or the overlapping area between two plates. This means that when our device is bent, the connection between the island and the gate and the island and the source is not changing, but the connection area between the island and the drain increases linearly. Then our model for what is happening experimentally is the following. When the junction is broken, somehow a graphene island is formed, and this island remains and this island remains weakly but physically connected to one of the electrodes that we identify as the source. But the island is not physically connected to the drain. So then when we close the gap, we find the same behavior that we found in our previous work. The island and the drain overlap each other, and the overlap area, and therefore the capacitance, increases linearly with the displacement of the device. Okay, so qualitatively speaking, the capacitance measurements are consistent with our model. What happens with the measurements of the differential conductance? In these measurements, we can identify very big resonances that change their height and width as the gap is closed. The height of the peaks first increase and then decrease as we close the gap. And this might seem a little bit counterintuitive, as we would expect that as we close the gap, the connection between the island and the drain continuously increases, and that led to a continuous increase in the conductance. But this is not exactly how it works. Actually, the resonances has this dependence to the gammas. That means that maximum in height is obtained when both gammas are equal. Then, in our experiment, gamma D should start well below gamma S, and then as we close the gap, it becomes similar to gamma S and then larger than gamma S. Okay, to know if all this is true, we have to put some numbers. For this, we perform tie-binding simulations with graphene and obtain the transmission coefficients, and from them the gammas of different devices devices with the transport code GOLO. We simulate islands with regular or irregular shapes and with a similar size to that proposed by experiments, and connected through a neck to the electrodes of a given width, or overlapping the leads a given distance d. Here I show just the values of gamma d as a function of the overlap, and we see that the gamma presents oscillations that were already expected. As I showed before, they were already present in the conductance calculations of our previous work and are due to quantum interference effects. And then the maximum of the oscillations can be fit, at least within the displacement range of the experiments, to this power law. So then we use this power law to fit the conductance as a function of the distance to the experimental data. And we see that we have a very good agreement although it is done with, the fitting is done with one free parameter, the gamma S, that is the physics electronic coupling to the source. From the fitting, we obtain this value to be of around 0.1 microelectron volts. And from the calculations of islands with different connection widths, we can estimate that the island is connected to the source via an echo of a few nanometers.
You have 2 minutes,
So
sorry.
Okay, just I'm already finishing. So then, just as a short summary, the final message is that we report here results of a quantum dot obtained in open air in a graphene break junction. And in this device, the capacitance and the electronic coupling to the drain can be tuned mechanically due to the change in the dot drain overlap by several orders of magnitude. And this work has been recently published in this reference. And with this, I finish. So thank you very much for listening, even being Friday. Thanks.
Thank you. Thanks. Very interesting results. Again, everyone, you can use the chat for questions or open your microphone if you want directly. I don't see any hands or any question yet. I will start then with the question. I mean, it's very, I think, basic because I want to understand your experiment. So basically you bend until it breaks, right?
Yes.
And then, yeah, then you, all the measurements are done with no deformation, basically, right? When you remove this bending or...
Yes, I mean, the thing is that the idea is that when you bend the first time, it breaks, and then somehow it expands a little bit, and then when you unbend, you don't just connect the
Yes.
two electrodes at the point, but one overlaps over the other because they are a little bit longer than before.
I see, yeah. And so there I have a couple of questions then. One is that, because you, again, your graphene is encapsulated, right? Between the, it was, I don't remember anymore, it was graphite, you said?
It's over insulating
Yes.
layer, but there is nothing above.
There is nothing on top. Ah, okay, I thought there was some, because then I was wondering what happens when everything breaks.
The lowest part is the flexible part, and then you don't have anything that actually constrains the displacement of graphene in this device.
Yeah. And then the other thing I was wondering is if you tried to see, to do some kind of imaging of the device afterwards, or yeah, to see that actually how
yes, there are images. Actually, I don't have them here, but there are some images. But yeah, you mainly see it. I mean, I think there are images, but just for the broken. But it's not like something that you can easily see. The overlap is not easy.
You cannot see it. Okay.
It's not so easy.
Yeah, and my
you don't have high definition images. You don't have it. It's not possible.
Yeah, I can imagine it's quite difficult, but I was thinking, well, yeah, I don't know, STM, or I mean, if you could do it in situ somewhere in an STM or something. And then... Looks
like they don't have all the devices that they need to do
this.
this.
Yeah, I can imagine, yeah. I wanted to say, the other question was like, just to see, yeah, it's a very practical things, like how many devices did they try? I mean, how reproducible, let's say, these things are.
I mean, this the first part, the quantum interference, is something that is quite reproducible, not in all devices, but happens a lot. The quantum dot is something that just happened in one device.
Okay.
Because actually, it's something that you we say that okay, somehow an island is formed there, but it's not something that you expect to happen all the time. And by now, there is no control over how to do it to actually happen. It just happened.
Yeah. Okay.
Okay.
Yeah. Thank you. Yeah. I don't know. Again, we have 1 minute left. for questions. Today everyone is very shy, I think, or tired, or a combination of both. I don't know. Okay, if not, we thank you again.
Thank you.
And we move to the next one is Irian Sanchez Ramirez.
Yeah, hello
Hi.
everyone. Okay, I will share the screen.
You can share your screen.
Okay, so, okay, so I'll start now, okay?
Thank you.
Okay, so good morning everyone. Welcome to my mini colloquium. My name is Irian Sanchez Ramirez, and the colloquium is titled Vacancy-Induced Phonoresonances in Graphene Nanoribbons. What I'm about to show you has been a huge part of my baccalaureate thesis, and because of so, the first thing I want to do is to thanks to my supervisors because of their hard work and patience put into this. Their names are Leonard Chico, Elena Diaz, and Francisco Dominguez Adame. And also I wanted to thanks to everyone in the Quantum Nanosystems group at the Universidad Complutense de Madrid, and especially to Yuri Kobaba, who taught me Quant, which is the main tool I use for numerical calculations here in this work. So moving to the outline, the structure of this presentation is going to be really simple. First, I will make a briefly introduction explaining what are the motivations of this work. And then I will summarize the model and the method used for obtaining the results that I will later discuss in the next section. Then I will make a brief summary of the results and observations and put it as a conclusion. So what's the aim of this work? Okay, the aim of this work is mainly gain a deeper understanding on electronic transport in graphene nanoribbons, and in order to, in near future, apply them into developing new graphene-based technologies. With this in mind, and since we know that point defects are likely to appear during the production of graphene nanoribbons, and that they can have a huge impact, or well, can have impact in the electronic transport properties, we thought that studying the point defects and the effect of the single vacancies on the conductance and local density of states in both armchair and zigzag nanoribbons could give us a clue of how this transport works, that we are assuming that's ballistic, since as said in the work of Baringhaus, it's true even for room temperature in graphene nanoribbons. For the simulations and numerical calculations, we are introducing single vacancies like shown in this picture, that we are assuming that they do not cause reorganization or reconstruction. And also we are using a quite new tool for this numerical calculation that is called Quant, that I will discuss later. So moving on to the model, for the purpose of this, or understanding the electronic transport, for understanding, the electronic structure in graphene, we used a one-band nearest neighbor type binding model, which Hamiltonian is written here. As you can see, we set the on-site energy to 0. Then we extended this sum only to nearest neighbors. And then this T is the hopping parameter between nearest neighbors atoms in graphene that will be from different sublattices. And then AI DAGA is the creation operator of the ith pi orbital in the sublattice A, and B, J, is the annihilation operator of the jth pi orbital in the sublattice B. So we chose this model because, since to our scope, that's a basic numerical calculation. It gives reasonably good results according to the experimental data and also the literature. On the other hand, since we're assuming ballistic transport, as I told you, in order to understand this phenomenon, we are going to use the Landauer formalism. So we are understanding this transport phenomena as a scattering problem. As you can see here, the conductance is quantized in the quantum conduction, as Vito told us, and is related with the transmission. So once the theoretical model is set, I'm going to show you how we proceeded. We focus the study on the low energy region of the conductance because it's where the effects of vacancies is greater. And what we did is to systematically introduce vacancies in different type of nanoribbons and in different positions and sublattices, and then study their conductance, local density of states, and then compare them. And for this, what we used was Quant, as I was telling you formerly. And we choose this package because it's open access and it's really accessible, and it's focused on tight binding models and especially in quantum transport. For the study and simulations, we studied infinite graphene nanoribbons of constant width, and we divide them in 3 parts. One central part of length L and width W, that's the conductor or scattering region, where we introduce the vacancies that is connected to the left and right to 2 semi-infinite pristine leads that are connected to a source drain gate voltage. For the results that I will discuss now, first I want to tell you how I'm going to proceed showing them. We will first take a look on the results and make a brief summary of observations, and then I will try to make some conclusions and make some explanations for these observations. Also, I want to tell you that the study is going to be separated for zigzag nanoribbons and Antwerp nanoribbons because they have a really different electronic structure in the pi orbital. And in the both edges, we are proceeding like the following. We first are going to take a look on the whole energy region of the energy spectrum of the conductance. Then we are going to focus on the low energy region of the conductance, and then we will try to relate all these effects of the vacancies on the conductance with the local density of states of the adjacent cell of the vacancy. So first of all, I'm going to talk about the Antwerp nanoribbons. And in this case, we studied a metallic Antwerp nanoribbon of a width of 20 dimers, as we can see here. And what you can first think, or at first glance, what you can tell is that a vacancy can lead to the appearance of a resonant dip at 0 energy. Also, there's quite of problems in the transmission, but it's not suppressible. I mean, the stir-like structure is still conserved, but we see that there is a resonant dip at 0 energy. But this resonant dip doesn't appear when the vacancy is located at a dimmer that's multiple of 3, as we can see here. N equals 3 and L equals 9, that's N equals 9 and N equals 3, we don't have this resonant dip at 0 energy. Another two interesting observations we can make, following to the next slide, is that the effect of the conductance of a vacancy located at a distance d above the center of the ribbon is the same as the effect on the conductance of a vacancy located at a distance d below the ribbon. This is shown here. We are, as in the last slide, we are simulating a 20 dimmer with Antwerp nanoribbon, and we are placing a vacancy in the 7th dimmer and in the 13th dimmer. That is 3 dimmers distance from the center. We can tell that the shape of the conductance is the same. Also, what we can see in this picture or in this figure is that the effect of conductance is independent of the vacancy of the sublattice. We could place here a vacancy at 7A and the effect would be the same. But yeah, that's a lot of observations, but what's happening? What can we say about it? First, for explaining this independence of vacancy sublattice, I will relate to Bahamon's work with a great paper shown below. This is because both of the edges participate in the edge. Both of the sublattices participate in the edge, and then the boundary conditions are conditioned by that. Why? Why are the boundary conditions so important? So all these observations are giving us some clues about how these transverse modes that carry the current behave in Antwerp nanoribbons, and they are of course affected by these boundary conditions. What we can first say, just by looking at this, like it's the same, is that these transverse modes are symmetrical from the center of the ribbon. That's because any vacancy you can place at a distance d far below or up of the center of the ribbon has the same. And also, if we remember what I told you later, that's the effect on conductance on the low energy regime doesn't show any dip if the vacancy is located at n equals 3. Is because these transverse modes has a periodicity, and the nodes of this periodicity are located on the places where the n is multiple of 3. But now, for a better understanding of this, we are going to focus on the low energy regime that I will show now. So what we can tell is that all the vacancies provoke a really similar shape for a resonant dip, but and it's really similar to the one appearing in the infinite graphene sheet as said by Orlov when they provoke a localization around the vacancy. And the width of the dip is the same for all vacancies except for the one in the first. So for understanding this and with the clue of this, that the width of the vacancy is very similar to the infinite graphene sheet, we are going to take a look of the local density of states along the conductions. What we can tell here is that there is a huge localization within the vacancy that within the sublattice that doesn't host the vacancy. Here's the sublattice A because the vacancies are located in the sublattice B. And then we can relate these peaks on the local density of states of the adjacent cell with a quasi-bound localized state that has zero energy, that's the resonant energy. So what's happening? These dips are really fun anti-resonances that arise due to the interference between the extended state that I told you later with these symmetries, etc., and this localized, semi-bound localized state around the vacancy that's localized around the vacancy. Roughly speaking, the resonant dips are due to the interference of the two paths of the electron can take. In one, the electron doesn't interact at all with this bound state, but in the other one, it interacts with this bound state. That's why we can now say if whether the interference is bigger or lower just by looking at the width of the minima. I will tell it later if I have time, but I think I'm short of time. So I will be moving now to zigzag nanoribbons. In this case, we're studying a nanoribbon of 16 dimers width, and we can tell that the resonant dip that appears at low energy is really dependent on the vacancy sublattice and the distance from the edge. So we are directly focusing on the low energy regime. And the first thing that I can say is that the effective conductance of eliminating an atom of a sublattice, let it be the sublattice A, at a distance d from the edge formed by the sublattice A is the same that would appear if we eliminate an atom in a sublattice B at a distance d of the sublattice B. As we can tell here, we are eliminating an atom in the dimer 6b, and we are eliminating at 10d. That's 6 dimers from the edge. So also the effect on conductance, we can tell that it's bigger if the vacancy is located near the center of the ribbon, as we can tell here, where if we place the vacancy at n equals 7b or n equals 7a, we have a wider dip of the resonance. A wider dip, and the energy of resonance is near zero. And what we can tell is that when we displace this vacancy from the center to the edges of the ribbon, this resonant energy is starting to get higher, and it's nearly, or when we place it in 1b in the edge of the ribbon, which the resonant dip is really narrow, and it's mainly in the threshold energy of the second mode. Also, the effect on the vacancy is only appreciable if the vacancy is located near the edge that's formed by this sublattice. What I mean here, that if we place a vacancy of n equal n 1a, we are not seeing any effect on the conductance at all. But why is it happening? Why does it happen? So all these observations are leading us to one conclusion that it's pretty clear. That's the edge states are the responsible of the transport at low energy, as said analytically by Wakabayashi. But for that, I will please take a look to the profile of the transverse wave functions in the zigzag nanoribbons. There are localized states at the edges of the ribbon. That here is the HB and here's the HA, and they are localized here, and they decay exponentially into the bulk of the ribbon. So what's happening here? What's happening here is that the overlap between these wave functions of the localized states are granting for zigzag nanoribbons of a channel at low energy for electronic transport. What's happening really is that even though the peaks on the electronic charges, the peaks of the density of electronic charges is peaked on the edges, the current density is picked on the center of the ribbon as told by Sarbo et al. Because we are using a first neighbor type binding model, and there's the only region where an electron can jump between two pi orbitals from the sublattice A and the sublattice B. So we are also having results according to Sarbo's work. That's also mentioned formerly. So for a better understanding of the influence of the H states and appearance of the resonant dips, and in order to compare them to the obtained results in arch-general ribbons, we did the same as we did for arch-general ribbons, and we also see
Sorry,
that.
you have 2 minutes?
Okay, fine. We can see that there are two resonant dips that are displaced from the zero energy, and that the peak that arises is not completely localized within the sublattice that doesn't host this vacancy. It's also localized in the sublattice that doesn't host this vacancy. Also, but it's more pronounced. That's more pronounced even if we are near the edge. That here, if we can tell n equal 4. The localization is more localized in the vacancy that doesn't host the vacancy, sublattice that doesn't host the vacancy. The resonant dips are wider, and the resonant dips are near the zero energy. What's happening here? We are also having a localized state provoked by the vacancy, but the effect of the boundary conditions are making those localized states not to be, or they are distorted by the boundary conditions because they cannot be located around the vacancy. They have to be located in the next nearest neighbor. So the resonant energy is displaced, and then if we treat it as a finite resonance, the coupling between the standard state and the localized state, and then the interference between them is way lower. So then I'm getting to the conclusions. That is here. Sorry for I ran out of time. These are the conclusions that you can read, and thanks all for your time. That's it.
Thank you.
Sorry.
Yeah, you still have a few minutes. We have some time for a couple of minutes for questions.
Okay.
Yeah, anyone from the audience? I think really today that everyone is too tired. Yeah, I will start again in the meantime. There is a question from Tineke. Tineke, you can open your microphone if you want and ask directly.
Yes, on your slide, I think it was 15. So you show these two edge states that are localized.
Yep.
I'm used to when you have two opposite edges, you have two opposite spins. If you look at the spin polarization, so maybe I missed something. But what does the spin do here? Do you know it? And if it wants to move through the overlap, for example, does it have to flip spin in case they are of opposite sign?
Okay, so you are okay. You are asking me about the spin. Well, I didn't consider the spin here because the Hamiltonian that we are using doesn't consider the spin. I know that at the edge of the zigzag ribbons there are polarized magnetical states, sorry, with the spin. But here, really, the states at the if that makes sense, the states at the edges doesn't contribute. I mean, they are the ones that are localized here doesn't contribute to the okay. I know what you are asking. I don't know if there's a spin flip here. Because we are just studying nearest neighbor type binding without the spin. There's the reason why sorry. We don't consider the spin, so I don't know how to answer you. I would have to study it. Sorry.
Okay.
Anyone else? Yeah, maybe just related then, is it possible with this software that you use to either consider this case, as it was mentioned, of the spin polarization, or I was wondering also if you can, instead of doing a vacancy, you can do a defect, or a defect, or like a dopant, or other type of defects?
Yeah, sure. Indeed, my colleagues at the the group, they study the spin effects, but I didn't consider it. You can study whatever you want. You have complete access to the positions of the graphene nanoribbon. And the next thing we are going to work is making a defect using silica and studying how is these resonant dips that also appear. And yeah, you can treat it perfectly. And I will also like try to answer to Tinker. I think that the spins has to flip because, of course, if we are considering just hopings between the lattice B and the lattice A, and they are polarized, even I don't know if when the state penetrates into the bulk, the spin flips. But in the case that it doesn't flip, that we are at 0 temperature and there is no perturbations, I think yeah, it should have a spin flip for transport, which means that the mobility maybe is decreased, but I don't know. Sorry for.
No, it's good.
Thank you, trying.
Yeah. Thank you. Thanks.
Thank
I think we're quite on time then to we finish this first part of the morning session. So now, Claudio, if you want to take over.
Yes.
Yeah.
Yes. Okay, so now we move to the second part of this session. I will share the program just to highlight a couple of changes in the program. Let me see if I can. Okay.
Yeah. Should be able to. Yeah.
Okay. Yeah.
It's coming. Yeah.
Do you see it? Okay.
Yeah.
So just to highlight these changes. So first of all, David Hagenmüller will replace Guido Pupillo. So the talk and the topic is the same, but Guido had the problem. So David will give the talk, and thank you, David, for coming. And then finally, there is a swap between the talk by Giuseppe Cerardo and Francesco Mattiotti. So the talks are the same and the titles and the topics the same. It's just a swap. Okay. So I think we can start with David Hagenmüller, who is going to talk about this idea of using a cavity to enhance superconductivity. This is an invited talk, so we have 30 minutes plus 10, and David, I will give you an alert when you have 5 minutes left. Okay.
Okay.
Stop sharing. Okay.
Screen. Can you see it?
Yes.
Yes.
Okay, good. So good morning, everyone. So I would like to thank the committee for organizing this nice online conference. Also, thank you for the invitation. I also speak in Guido's name, of course. So this gives me the opportunity to present some recent results about cavity-enhanced superconductivity. So these results are mainly experimental, and so this has been a long-lasting project that started in Strasbourg more than 5 years ago. With the simple question, can one modify the superconducting properties of some material by coupling its phonons to a resonant cavity? So the experiments were carried out in Strasbourg by the group of Thomas Ebessen, and have involved several postdocs and PhD students over the years. On the right side is a photo of the theory group I'm working in the same institute. So we started collaborating with Thomas on this project last year. And these are my collaborators, Guido Pupillo, Johannes Scharfenmeier, and Stefan Schütz. So this is the outline of the talk. So I would start by introducing some general concepts of cavity quantum electrodynamics. In particular, I will talk about an important regime, which is called the strong light matter coupling. I will then introduce different kind of hybrid light matter quantum states, which are called polaritons, so exciton polaritons and phonon polaritons, which typically occur in the strong coupling regime. Then I would explain how one can exploit the properties of these phonon polaritons to modify conventional superconductivity. So I would start by general considerations, then I will show you the experimental results, and then I will show the simple theoretical model that we have used to understand at least partly the experimental data. And I will finish by the conclusion and giving some perspectives and open questions. So the usual way to introduce the strong coupling regime of cavity QED is to consider the simplest model of an atom, which consists of a ground state G, an excited state E, separated by the transition frequency omega naught. And the transition between these two levels corresponds to a dipole moment, which can be coupled to the vacuum fluctuation of the electric field confined in a cavity made of two mirrors. So this light matter coupling is quantified by the vacuum Rabi frequency, omega, and the strong coupling regime is achieved when this vacuum Rabi frequency exceeds both the cavity and the atom decay rates. So in this case, the cavity mode and the atom can exchange energy in a quasi-reversible way, which is described by the famous Hamiltonian introduced by Jensen and Cummings. So the first two terms here describe the energy of the atom and the resonant cavity mode. And this coupling term describes the energy exchange processes. So starting with the atom in its excited state, the probability of staying in this state oscillates in time with a frequency omega before being damped, which is called vacuum Rabi oscillations or single photon Rabi oscillations. It's also interesting to look at the spectral features of this system by measuring, for instance, the cavity transmission spectrum. And instead of a single peak at the cavity mode frequency, one would measure two peaks separated by a splitting, which is twice the vacuum Rabi frequency. So these two peaks correspond to hybrid light matter quantum states, which are called polaritons. And these features have been first observed with Rydberg atoms or cesium atoms by the group of Serge Haroche in Paris and Jeff Kimball in the US. But one could also wonder whether the strong coupling regime can be achieved in solids instead of atoms. The main drawback, however, is that the decay rates in solids are typically much larger than in isolated atoms because of electron-electron and electron-phonon interactions. But the big advantage of solids, though, is that they contain a macroscopic number of carriers that can collectively couple to the electromagnetic field. So in this case, the vacuum Rabi frequency is enhanced by a factor square root of n, where n is the number of coupled excitations. So this can help outweighting losses and then help reaching the strong coupling regime. So historically, the strong coupling regime in solids has been first achieved in quantum wells, which are semiconductor heterostructures. So in this case, one can couple the transition between the valence and the conduction band of the semiconductor host. And the excitation coupled to light is a superposition of electrons and holes bound together by Coulomb interactions, which is called an exciton. So when the density, the exciton density is sufficiently small, excitons behave as bosons, and one can think of the exciton-photon coupling as two coupled harmonic oscillators. So as for atoms, this coupling gives rise to two polaritons separated by a splitting, which is twice the collective vacuum Rabi frequency. And the strong coupling between excitons and photons has led to remarkable developments over the past decades. And perhaps one of the most impressive is the realization of Bose-Einstein condensation of exciton polaritons at Kelvin temperatures instead of millikelvin for bare excitons. So this is because the lower exciton polariton can be seen as a dressed exciton, which inherits the very small effective mass of cavity photons. So this reduction of the effective mass leads to an enhancement of the critical temperature for Bose-Einstein condensation. But here, I would like to focus on another type of excitation, phonons, which can be also strongly coupled to light. So in a polar crystal, for instance, two ions with opposite charges in the same unit cell can oscillate around their equilibrium position along the direction which is perpendicular to the propagation. So this is called the transverse optical phonon, and these transverse optical phonons can be efficiently coupled to infrared light. In this case, the vacuum Rabi frequency is proportional to the ionic plasma frequency, which is defined here. And since phonons are bosons, one can also think of this coupling as two coupled harmonic oscillators, which gives rise to two polaritons. So we call them phonon polaritons. And the energy dispersion of these phonon polaritons can be obtained from the Helmholtz equation here with a dielectric function of this form. So this is what the typical energy dispersion of phonon polariton looks like. At large wave vectors, the upper polariton is light with linear dispersion, while the lower polariton goes asymptotically to the transverse optical phonon frequency. On the other hand, at small wave vectors, the lower polariton is light, while the upper polariton is shifted to the longitudinal phonon frequency. And this shift provides a band gap, which is usually called a Strahlen band, where no mode can propagate in the Borg crystal. So this means that one would measure a reflectivity 1 in this frequency range when probing the system with incident light. And importantly, the extent of this Strahlen band is proportional to the strength of the phonon-photon coupling, which is itself proportional to the ionic plasma frequency. And since these polaritons can be seen as dress phonons with modified frequencies, a natural question is then, can these dress phonons lead to a modification of electronic quantum phases governed by the coupling to phonons, such as superconductivity, for instance, conventional superconductivity? So this question is somewhat similar to the one at the heart of Andrea Cavalieri's experiment in Hamburg, to whether one can modify or even induce superconductivity using short laser pulses addressing some particular phonon mode. But here, the main difference is that these experiments involve out of equilibrium superconductivity, while our purpose is to address superconductivity at equilibrium. So before I move on with this idea, I would first like to recall some basic properties of superconductors. So there is a microscopic theory derived by Bardeen, Cooper, and Schrieffer in 1957, which allows to describe most of the superconductors based on simple metals, which are called conventional superconductors. While above the TC, electrons undergo collisions with the crystal impurities, which gives rise to electrical resistance. Below the TC, electrons in a superconductor can bind together, forming Cooper pairs, which can flow through the crystal without dissipation. And one of the most important ideas of this theory is that the Cooper pairing mechanism depends on the electron-phonon coupling. So when moving through the lattice, an electron induces a deformation of the lattice, which can then attract another electron and eventually overcome Coulomb repulsion. And in a conventional superconductor, the TC depends on two parameters. So the average phonon frequency, which is essentially the Debye frequency in the simple BCS model, and the strength of the electron-phonon coupling, which is usually described by this dimensionless parameter lambda. So the larger are these parameters, the larger is the TC. And if one assumes that a spherical Fermi surface and one longitudinal phonon mode with a frequency omega q, the electron-phonon coupling is described by the Fröhlich Hamiltonian, and the parameter lambda can be computed by averaging this electron-phonon coupling over all processes where electrons are scattered across the Fermi surface by absorbing and emitting phonons. So in the end, lambda is given by this formula, where GQ is the electron-phonon matrix element and KF is the Fermi wave vector, so the radius of the Fermi surface. And one can see directly from this formula that the reduction of the longitudinal phonon frequency would lead to an enhancement of lambda, which in turn would lead to an enhancement of the TC. And as I explained before, so a possibility to reduce this longitudinal phonon frequency could be to exploit strong coupling to cavity photons, since the lower phonon polariton lies below the longitudinal phonon frequency for all wave vectors. But unfortunately, it turns out that it's not that simple. And the main reason is that superconductors are metallic materials and not ionic crystals. And then the ionic charges are efficiently screened by the free electrons. So this means that phonons in a superconductor are only weakly coupled to light, or in other words, the Strahlen band in the superconductor is vanishingly small. So this means that there is no phonon redshift, at least at large wave vectors, comparable to the Fermi wave vector. And the only region in K-space where one can have a sizable phonon redshift is at optical wave vectors, so close to the light cone. So yes, and if we assume, to simplify, that the electron phonon matrix element is practically constant over the whole range of wave vectors, we also assume that the longitudinal phonon frequency is constant, then one can see directly that this phonon redshift at optical wave vectors only makes a very small contribution to lambda. So in order to circumvent this issue related to the intrinsically weak coupling of phonons in a superconductor, Thomas Ebbesen got the idea of using another material, so here a polymer, which is itself strongly coupled to light and could effectively mediate a strong coupling between the superconductor and the cavity. So more precisely, they used a superconducting powder of superconducting material dispersed in a polymer matrix and then coated by a thin metal layer. So this metal layer is used to generate confined modes of the electromagnetic field at the interface between the metal and the film, which is essentially dielectric here, since the amount of superconducting material used in the polymer is typically small. So these confined modes of the electromagnetic field are called surface plasmons, and here they play the role of the cavity photons. So the idea of the scheme is shown here. Phonons in the superconductor are only weakly coupled to surface plasmons, but they also interact directly with polymer vibrations through a dipole-dipole coupling. So on the other hand, the polymer is chosen such that one of its vibrational bands is strongly coupled to surface plasmons. So the idea here is really to use these two types of interactions to effectively induce strong coupling between phonons in the superconductor and surface plasmons. So in order to check this idea of cooperative strong coupling, they first consider an organic superconductor, which belongs to the class of alkalidope fullerenes. In this case, it's rubidium-3C60. So this compound becomes superconductor below Tc of 30 Kelvin. And in particular, there is a vibrational mode of the C60 molecule, which is expected to play an important role in the onset of superconductivity, so meaning a large electron phonon coupling. And as a polymer, they chose polystyrene, which features a vibrational mode of the phenyl group, which is quasi-resonant with the mode in rubidium-3C60, which is involved in superconductivity. So here I show you the infrared spectrum of the two compounds, showing the overlap between the two vibrational modes. So I will come back later on why these two modes need to be close to resonance. So these modes are also interesting because they're both infrared active, and then they can be strongly coupled to surface plasmons. So here I show you the reflectivity spectrum of a sample, which allows to characterize the polariton dispersion as a function of the in-plane wave vector or the incidence angle. So the thin dashed line here is the infrared spectrum of polystyrene that I showed you on the previous slide. And the thick dashed line is the dispersion of surface plasmons, which is linear close to the light cone. So when these two lines cross each other, vibrational modes and surface plasmons hybridize together, which gives rise to these polariton branches. So the empty circles are for the film with only polystyrene, and the filled circles are for the film which contains both polystyrene and rubidium-3C60. So the first thing we see is that the Rabi splitting in the vicinity of this resonance is larger than the line width of the uncoupled modes. So this means that we are in a strong coupling regime. And on the other hand, we see that there is practically no difference between these two sets of data, which means that phonons in the superconductor don't play any role in the strong coupling of the film, as we can expect from the general arguments that I explained before. So now they investigated the superconducting properties of the samples, and in particular the critical temperature, by doing magnetometry measurements. So an important characteristic of superconductors is that they exhibit perfect diamagnetism, so they fully expel an applied magnetic field. And this means that the magnetic susceptibility in a superconductor as a function of temperature looks like this. So it drops to negative values below the critical temperature. So here are the results of these magnetometry measurements. So in order to check this cooperative strong coupling mechanism, they prepared different kinds of samples. So the first one has no metal layer in the absence of surface plasmons. And the second one has no auxiliary coupler. So in this case, they just replaced polystyrene with an inactive polymer, PMMA, which does not have any vibrational band overlapping with the mode in the superconductor. And in both cases, we see that the TC is 30 Kelvin, so it is not modified as compared to rubidium-3T60 alone. And it is only when both polystyrene and the metal layer are present that the TC is actually enhanced to 45 Kelvin. So this is a 50% increase of the TC. And I would like to emphasize here that there is no external laser or light used in this measurement. So this is really an effect of the vacuum electromagnetic field. And next, they investigated another very different superconductor, YBCO, which is an unconventional high TC superconductor. And in this compound, there is an infrareactive mode, which corresponds to the vibration of the apical oxygen atoms. So this is exactly the mode which was targeted in Cavalieri's experiment. So this mode is somehow expected to be involved in superconductivity in this compound. And they were able to use another mode of polystyrene at lower frequency, which is again quasi-resonant with the mode of YBCO. So they use exactly the same scheme. Here I show you briefly the polariton dispersion, showing strong coupling of the YBCO films. And these are the results of the magnetometry measurements, so the magnetic moment as a function of temperature. And surprisingly, in this case, instead of an enhancement of the TC, they measured a reduction of about 6 Kelvin. So again, only in the films which contain both polystyrene and the metal layer. So of course, superconductivity is already quite complex and controversial in YBCO, even without cavity. So we don't understand why we observe a reduction of TC in this case. And I will be happy to discuss this with you after the talk. But for now, I would like to move on and show you the simple theoretical model that we have used to understand the cooperative strong coupling mechanism in more detail. So this model has 4 copper coupled harmonic oscillators. So 3 plasmons in the metal layer, which correspond to collective oscillations of the electron density, 3 photons with linear dispersion, and 2 types of phonons, so 1 phonon mode in the superconductor and 1 phonon mode in polystyrene. So we consider the film as an effective homogeneous medium on top of the metal layer. And in addition to the phonon frequency, this model has 3 parameters, 3 independent parameters. So the superconductor and polystyrene filling fractions in the film, which we call F and then 1 minus F. And the 2 ionic plasma frequencies for each type of phonon. So I remind you that these the strength of the phonon-photon coupling is proportional to these ionic plasma frequencies. And since the in-plane wave vector is a conserved quantity in this model, one can decompose the Hamiltonian into each subspace with a given in-plane wave vector. And in each one of these subspace, the Hamiltonian has 3 contributions. The first one is the contribution of 3 photons with a linear dispersion, as I said. The matter Hamiltonian includes the contribution of the 2 types of phonons and plasmons in the metal layer. So I will show you this one on the next slide. And the coupling between light and matter degrees of freedom. So so importantly, the surface plasmons that I mentioned before are automatically taken into account in this model through the coupling between plasmons and photons. So the matter Hamiltonian includes the contribution of the 2 types of phonons, so in the superconductor and in polystyrene, the contribution of 3 plasmons, in the metal layer. We also have a direct dipole-dipole coupling between the two types of phonons. So this one plays a very important role. I will come back later to this. And we also have, so each phonon dipole moment interacts with its own field, which is usually called dipole self-interactions. So these are the two terms here. So it is interesting to first look at the effect of these dipole self-interactions and diagonalize the first line of this Hamiltonian. And by doing so, we obtain this new matter Hamiltonian. So this is essentially the same one as here, but written in the new basis. And the new phonons here with the tilde are blue shifted with respect to the bare phonon frequencies. So this blue shift depends on the ionic plasma frequency in each material and the film fraction, the associated film fraction. So this dipole self-interaction, they're just the microscopic mechanism which gives rise to the phonon Restrahlen band. So here, the shifted frequencies with the tilde play the role of the longitudinal phonon frequencies, while the bare frequency play the role of the transverse optical phonons frequencies. And importantly, these shifted frequencies are the ones that are measured, that are probed by light coming at normal incidence. So there is a very small wave vector, as you can see here. So they precisely correspond to the peaks in the transmission spectra I show you before when discussing the experiment. So here what we do, we consider exactly the conditions in the experiment. So we assume a resonance between the two shifted phonons. We also assume that the ionic plasma frequency in the superconductor is very small compared to that of polystyrene. And we assume that the filling fraction of the superconductor filling fraction is very small. So this is in agreement with the experiment, experimental conditions. So this means that in this case, the Restrahlen band of the superconductor is very small compared to that of polystyrene. And this means that polystyrene actually completely dominates the coupling to light. So one can look at the polariton dispersion in this case. So this is obtained by diagonalizing the full Hamiltonian I've shown you before. So the two high energy polaritons here and here, P3 and P4, stem from the hybridization between plasmons and photons. But more interestingly, we have also two low energy branches, P1 and P2, which correspond to the dress phonons. And importantly, the lowest energy polariton here, P1, is very close to the bottom of the polystyrene Restrahlen band. So this is not very surprising since, as I said, we are considering the conditions where polystyrene completely dominates the coupling to light. But in this case, one could also expect naively that this polariton is fully composed of polystyrene phonons. And it turns out that this lowest polariton is actually only 50% polystyrene and 50% superconductor. So why? This is really because of the direct dipole-dipole coupling between the two types of phonons, which lead to phonon hybridization in the sample. And this holds as long as this resonance condition between the two shifted phonons hold. So this explains why this resonance condition is crucial in the model, in the experiment.
Sorry, David, you have 5 minutes left.
Okay, thank you. So in other words, one can really see this lower polariton as a dressed superconductor phonon with a lower frequency, which should lead to an enhancement of the electron phonon coupling parameter, and in turn an enhancement of the TC. So here I show you the relative enhancement of this electron phonon coupling parameter as a function of the polymer ionic plasma frequency, so the coupling strength of the polymer to light, the superconductor filling fraction, and the detuning between the bare phonon frequency. So one can see in this plot is that the electron phonon coupling parameter increases with the strength of the coupling of the polymer to light, and features a maximum at rather small superconductor filling fraction. So this is in agreement with the experimental data. Okay, so I'll now conclude. So we have shown that the critical temperature of two very different superconductors can be modified thanks to a cooperative strong coupling mechanism, which we have described using a simple theoretical model. But of course, this model is way too simple to directly predict how the TC is modified quantitatively. So, for example, it is known that electronic correlations play an important role, not only in YBCO, but also in the organic superconductor. So in the future, it will be very interesting to study whether strong light matter coupling can also affect these electronic correlations. It would also be interesting to go beyond the effective description and provide a microscopic description of the different type of interactions. For example, also this dipole-dipole coupling between the two types of phonons. So one could use, for example, ab initio calculation. That could be quite interesting. And there are also more general questions like, does this work with any superconductor or auxiliary couplers? What could also think of using another geometry. So instead of using a powder, one could use an heterostructure with thin films. And yeah, is there any limitation to this effect, and why does the TC decrease in YBCO? So that's all the open questions that we have thought of. So yeah, I'll stop here. Thanks for your attention.
Okay, thanks, thanks David for the nice and interesting work, which basically puts together optics, photonics, superconductivity. So it's very interesting. So now we have time for a few questions. So if you have anything to ask, you can use the chat, or you can directly jump in, opening your microphone or raise your hand. I mean, it's up to you.
I have a question.
Okay, Luca, please go ahead.
No, I was curious. Very interesting work. When you say that your model is too simple to predict the critical temperature, what do you think is missing in your model? Are you pursuing a different Hamiltonian? I mean, why your model is too simple to predict the critical temperature?
So I think the main point is really electronic correlations, I think, because as I said, in both cases, so in YBCO, well, this is well known, but also in rubidium 3C60, I mean, there are electronic correlations play a very important role. So this compound is quite close to mode state, a mode insulator. So I really think that including electronic correlation in the model would be a crucial step if we really are to make quantitative predictions.
Okay, thank you.
Sorry, David, but basically the electronic correlations enter in the screening processes in the sample.
Yeah, I mean they're entering really the prediction of the TC, I think.
Yeah, even though, yeah, predicting quantitatively TC in correlated materials, it's impossible even in normal conditions. So yeah, but you can probably predict the change of TC. Yeah,
exactly. Yeah, but I'm not sure if we will be really able to quantitatively predict exactly what is the TC in this condition.
Yeah, but at least the qualitative difference, yes.
Yes, sure.
Okay.
I have a small question, if possible. For the IPCO, then you say, you saw that there is a decrease of the critical temperature, right?
Yeah.
And I was wondering, I'm not familiar with the other, organic compounds, but in IPCO, we know that, for instance, the oxygen deficiency or structural defects, and I mean, that TC is quite sensitive to all these kind of things. So I was wondering if it could be related with that, the fact that it's a decrease that you observed. Although I remember, yeah, I don't know if you can show it again, there was only one, it was the case with the really, you know, in the cavity with the gold, right?
That's for YBCO, yeah.
Yeah.
But while the oxygen content doesn't change, I mean, it is the same compound that we use without the cavity and with the cavity. So,
yeah. No, okay, it could be, I was thinking, yeah, when you use the polystyrene or the PMMA, maybe there, I don't know if there is any kind of structural, you know, modification, but it is true that then, yeah, when you have the golds, the cavity, yeah.
So qualitatively, I mean, it's similar to what we did with rubidium 3C60. In the sense, we get the same trend. So in this case, the only difference is that it's a reduction of TC instead of an enhancement. But the reduction in this case is only there when really you have these two modes interacting with each other and the metal layer.
Yeah. Thank you.
So maybe this could be due to actually to electronic correlations. I think that
yes,
be an explanation if we include this.
And sorry, David, but in all these experiments, as you said, I mean, there is no external light, so the population of the cavity mode is the spontaneous population, the fluctuations of the population of the mode. So, do you expect that if you use an external driving field, so you populate this mode in a coherent way, possibly using short pulses, so you can populate this mode in a very effective way without heating up, at least for a few picoseconds? Would you expect an enhancement of these effects, or the way you populate the mode is not important in the mode?
That's a good question. Yeah, to be honest, I mean, we thought about this, and actually, I think Thomas has planned to address this question, so to try to populate this the cavity. But I really don't know if we would expect something. If we should expect a larger enhancement. This I will not be able to say yet.
Okay, thanks. We have time for another question if there is anybody willing to ask anything. Okay, if not, we can thank you again, David, for the interesting work. So thank you a lot.
Thank you. Thanks to you.
Okay. Now we move to the next speaker, who is Tineke van den Berg. So you can share your screen, Tineke.
Wait, I'm just going to do one little thing. Okay. So you see it here.
Okay, yes, perfect. Okay. So I give you an alert when you have 3 minutes left.
Okay. Okay. Let me just leave it like this. Wait. Okay. So you hear me?
Yes.
Okay, so yes? You can go?
Yes, please go ahead. Yeah,
okay.
Perfect.
So the work I'm presenting was done with, I now work in Spain, but it was done in Sweden with Peter Samuelson, who has published quite a lot on this subject with this group. It's about, it's a circuit QE system. So it's about charged photon counting statistics and correlations in conductor resonator systems. It's published in this article here, PRV. And I will see how I can do it. So as I said, circuit QD systems are systems where you have some superconducting cavity and you have something in it, something that's made up of matter, and you have light-matter interaction. So Peter has been working on this, had been working on that for a while when I came in this group. And he was in contact with the people in Zurich, and they had some experiments giving very large G2 factors when they were measuring photons coming out of the cavity, which is what got us interested in why do they get these large G2 functions. But apart from that, these type of systems are interesting because they are just a very, very well controlled in general, and so they're like a test bed for investigating light-matter interaction. Also now with current technology, things are getting better and better, and these things are always advancing, and so you have lots of possibilities. Possibilities are getting better, there's more possibilities, and so due to this constant evaluation, it's interesting to look at what can we do with these systems. So now they're also making very high impedance cavities where you get very large coupling between light and matter. In our case, we're interested in when this coupling, it doesn't have to be actually coherent. There just has to be strong coupling between light and matter. And then also the type of systems we were working with are microwave photons, and these were hard to measure before, but they're also, it's getting easier and easier to just measure single microwave photons. So things can be done today with these systems. Now, typically we will look into a system where you have just some single dot coupled to a single mode cavity, and it's leaky, so photons are going out, and we can measure those photons. In particular, we will look at a hybrid circuit QED system. First, people started using just superconducting systems, so some qubit in a cavity. And now, when you say hybrid, there's it's not just superconducting, there's something more, something else in it. And this can, for example, be some artificial dot, and it can have leads. So what's happening in these hybrid systems, interestingly, is that you have not only just light-matter interaction, but you can have transfer because you have leads. You have an open quantum system, which brings in new possibilities. And this was one of the first experiments in these type of systems, and it's a very nice paper. It's very elegant in general what can be done in these systems because they're so well controlled and can be made very clean. So people are doing double dots, single dots, photon-mediated transport between different dots, and in particular, Jason Pettis' group in America is also looking at spin qubits. Now, so, okay, I'm not going to discuss this in very much detail, but there's many groups working also on the theory. And Peter was one of them. He has a whole series of papers, so two of them were I was main author. And he has also been on some thermoelectrics together with these type of systems. It's really interesting. And then on the experimental side, so the main groups I would say is Takis Konto's group and Adek Ote's group in Paris. And there's a Chinese group now working on this as well. And then there's the group we were in contact with in Zurich, were doing nice experiments. And then Jason Pettis, he's been working with spin in general. Now, usually what people would do typically is they would shine light into a cavity, look at what is happening in the dots or in the qubits, and focus mainly on this, like what does the light do with the state of the matter part in your system, so the qubits or any kind of two-level system. Now in 2011, there was a paper, it was nicely called the bright side of the Coulomb blockade. And it was actually focusing on what was coming out of the cavity. I think they were still shining light into the cavity, but they were looking on what was transmitted, and they were focusing on the light, on the bright side of the problem. And so this generated a lot of interest. And so our paper is part of the series of things that came out after this experiment. And so there were people had been working on tunnel junctions, afterward double dots. Especially this paper is rather close to what we were looking at, although it's a double dot and they don't find the same features as we do. And then there's people with single dots, just like also what we're doing here. So now in the rest of the talk, I will introduce the system in a bit more detail. And I will discuss the theoretical tools and the results. And I will draw some conclusions in the end. So we have this single dot here sitting in the cavity, and it's attached. There's two leads attached to it, and so there's dots that can hop from the left, let's say, to the right. And when the electron comes in, and also when it goes out, it can absorb or emit photons into or from the cavity. And it's in the high bias limit, so it can be multiple photons. This number is ruled by the color factors. Yes, and this cavity is leaky, so things can leak out. So there's no energy constraints in how many photons it can. So we work in the high temperature regime, so that co-tunneling can be neglected, and we can also ignore coherent dynamics. However, temperature is lower than the resonance frequency of the cavity, so that no photons can just come in from the outside world. So we work in the theoretical framework of the master equation, and we will try to get out statistics and correlations, and we will, for example, look at the joint electron-photon dynamics, which is interesting because it can get you the cross correlations and the cross noise factors and noise cumulant. And so you have this master equation typically for this probability vector. So this probability vector, it is giving you information about, well, one of the components will give you the probability for n electrons being in the dot, which can be 0 or 1, because only one can tunnel through at the time. And then, having p photons in your cavity. So this p can go from 0 to watt, whatever. And that is given that conditioned by the fact that you've been measuring at time t, and while you were measuring, you have measured np photons coming out of the cavity, while ne electrons move through the dot. So this that's your probability vector, and it's raised by this equation. This is actually in Fourier space, so where you have these counting fields, electron counting field and the photon counting field. Now, we will generally be interested in long times, and then you can sort of say, okay, what's the probability of after a long time measurement having Ne electrons gone through the dot and Np photons in my cavity, photons measured, being emitted from the cavity. And then you sum over all these states, and you do it for long times. And this is it gives you the full statistics of your system. And these full statistics are reigned by this cumulative generating function. And this cumulative generating function, again, you can get it from your this matrix equation, where you have this is your master equation and matrix. Now, when you just write out this problem, it seems to be very complicated and it seems to be hard to solve, but actually it turns out there's one basis, the damping basis, in which things become rather transparent. This damping basis is the basis in which the leaking from the cavity part of your system is diagonal. And it's actually turns out that it was the first time I've seen this basis, but in quantum optics, this is a very regular basis to use. Now, so what you can do is you can solve these equations, and you can get out the lowest order cumulants. We are basically, as usual, interested in just mean current and noise, average current and noise. And so when you do this for the electrons, interestingly, you just get the mean current and the electron noise that you would expect for a single dot, without any cavity. So okay, that's rather surprising. Okay, it's probably due to asymmetry in your emitting and absorbing thing. And if you look at the damping basis, it's obvious that this is just like the way it should be. Also, what's very surprising is that the photon cumulants are just proportional to lambda squared times this electron current. And there's this 2 because you can both have photons coming in your cavity when you go into the dot or when you go out of the dot. And so this is all, there's no higher order terms. And also when you look at the photon noise cumulant, it's of order lambda squared. So it's this photon current times some photonic Fanon factor, which is 1 plus some quantity, which is actually, this is large, is always positive. So it turns out you always have bunching in the photon statistics. Now, interesting also. Yes.
You have 3 minutes left.
Okay. Oh, wow. Okay, so the electron photon noise, you can actually write it as just some lambda factor times this the electron noise, which shows a complete dependence on the electron statistics. Now you can look at this photonic factor. You see it's always larger than 2, and yeah. Okay, let me just. So these photons are always bunching. Now you can solve the full joint probability distribution. You can solve this order by order. Actually, you can go up to very high orders because it's also quite, things simplify a lot. We have only shown in our paper, for example, the first 2 cumulants because they, you can write them on a line, and the other cumulants become very complicated and very untransparent. So this is just, you see, no coupling, no photons. You have only something that depends on your electron statistics. Now, if you have coupling, you have single photon transfer. You see that for one, no, sorry, single photon transfer. Yeah, that's so you can see how this is done here. Now, in the large loss rate limit, you can solve everything. Everything becomes really simple. So this is a large loss rate. You get only this 2x2 matrix. You can solve the generating function. You can even solve this in the saddle point approximation very exactly. You see in the large loss rate limit, you can get for 1 electron jumping through your dot, you can get a whole cascade of photons, which is one of the origins of the bunching. Now, this is the full combined statistics. They're sort of somewhat hard to interpret, but what you see is that as you get larger coupling, your electron statistics become more spread out. In your photon statistics, there's some skewing, but also what you see, that the upper part is for small leakage from the cavity, the lower part is for the large leakage. You see that if you have small leakage, so the cavity gets filled up more, you get this larger spread of your statistics. Now, so the marginal distribution function, so only for electrons, there's no surprise. You get the usual single dot statistics, and the photonic marginal distribution function, you get this thing here. So this gives a Gaussian distribution, and it doesn't behave so surprisingly. So now this 2-point Glauber function, so you can put it in the damping basis, and things simplify a lot because you have your currents here, you have your current matrices here, and actually all the lambdas go away. It turns out that these Glauber D2 functions are completely lambda independent. And you can also solve this equation here, which gives you the cross noise as a function of your cross correlators, and which works very well. So the electron, there's no electron-electron G2 function, no surprise. Photonic G2 function, so you see it depends on the symmetry of your dot and on the coupling, sorry, it depends on mostly on kappa and leakage of your cavity and the coupling, dot tunneling rates. And you can solve this in a few limits, and you see that you always have bunching for your electrons. Now, in the case of the cross correlators, just I want to highlight one more thing, is it depends on, like, if you measure on the left or on the right. If you then this gamma goes to minus gamma, and so you see here it goes from bunching to anti-bunching, but that's just because it depends on if you do the measurements on the right side of your lead or on the left side of your lead. This exchanges gamma to minus gamma. And so in any case, we can get, for the photonic G2 function, we get we can get very high values, which was what they measured in Zurich at some point. And so what was interesting here is that you have these very specific expressions for your photonic cumulants and for your cross cumulants, and they are because of well, you can see in the damping basis that this just is the cutoff. There's no higher order terms. You always get electron anti-bunching, however, photon bunching, and these large G2 functions, which are independent of lambda. So that's, thank you for listening. And I'm 1 minute late.
Okay, thank you. Thank you for the talk, for showing these results. So we have time for one or two questions. So you can either type in the chat or switch on the microphone. Okay, may I ask you, just a curiosity, probably, I don't know if I missed something, but at some point you showed a sort of a funnel line shape. So there was a plot with the funnel.
Yes.
If you go back, okay. So
this one here, or
this one,
or maybe this one. This one.
Exactly. Exactly.
Yes.
So basically, in this photonic funnel factor, so basically you can tune the a sort of a symmetry of the funnel line shape.
Mm-hmm. So, yeah. So this symmetry of the funnel.
Because
okay,
I mean, usually I mean, in solid state physics, the funnel line shape is something which has an asymmetric line shape due to the interaction between a discrete level with a continuum.
Yes, yes. So
And by tuning, yeah, by tuning the overlap, you can also reverse the line shape, so you can have an anti-resonance or a resonance. So I wonder whether it's similar in this case.
Okay, so the funnel factor we have here is always larger than 2. It's always larger than 1. Sorry.
Okay.
There's always anti-bunching. Now there's another thing is that you see it depends on this gamma, which depends on the hoppings in your dot. And actually, it doesn't depend just on gamma; it depends on gamma squared. So it's how do you say it? It's insensible to how the symmetry of your dot is, right? If it's left or if it's right. And then, what should I say? Yeah, for very weak coupling, the funnel factor goes to 1. Yeah, so I don't exactly know what you mean with this. I mean, we have this dot which has this symmetry around the resonance level, because it can either absorb as many as it wants or it can emit as many as it wants, which is probably why we don't have the feature that you have, what you're talking about.
Okay. Okay, thanks a lot. So if there is any other question, you can ask now.
Yeah, I have a simple question. I was just wondering, because you mentioned that the G2 function is not affected by the cavity coupling.
Yes.
Can you remind me quickly, like, what are the observables that are affected by the coupling to the cavity?
Sorry, what were you or what were?
What are the observables that are affected by the coupling to the cavity?
Okay. Well, actually, the photon current depends directly on the coupling to the cavity. So the strange thing here is, well, strange. The surprising thing, I would say, is that this the dot is not affected by the coupling to the cavity. It's just like as a regular single dot without a cavity.
So the electronic current is not affected by the cavity?
No, which is surprising. And that I think is because it can absorb or emit, both when going in or out, any number of photons, but it can both absorb and emit, and it's somewhat symmetric with respect to this event. Surprisingly, the electronic current is not affected by the coupling. However, the photonic current is, and it is directly proportional to lambda squared. There are no higher order terms. So actually, measuring both these current can be used to extract the coupling strength.
Mm.
And then the G2 functions, they do not depend on lambda. So which means that even for very weak coupling, you can get large G2 functions, large cross correlations.
Okay, thank you.
Okay, I think we can thank the speaker. Thanks a lot. Okay, we move to the next speaker, who is Susanne Lederer.
Hi.
Hi, Susanne. Okay, so you can share your screen. Okay, perfect. Great.
Okay.
Okay, great.
Good. So.
Okay, go ahead. I'll give you an alert when you have 3 minutes left.
Okay, thanks. Okay, so thank you for giving me the opportunity to present my work here. My talk is about atomistic simulation of current-induced forces and atom dynamics and molecular junctions. And as an introduction to this topic, I would like to start with the example of electroburning, where currents are used to build gaps in, for example, here a graphene nanosheet. And so a high bias is applied to the graphene until a gap is formed. So until atoms start to rearrange and a gap is formed in the graphene. That's kind of what you see here. I hope you see my pointer. And yeah, so these nanogaps are really, they're very small, and they can be bridged by molecules, for example, to build single molecule junctions. And in a similar way, current-driven switches can be created. In this work here, for example, they could actually establish two states of low and high conductance, between which they can switch using the current. And so here you see this switching. It has a temperature dependence, which kind of supports their interpretation that in the gap there are carbon chains formed and broken. And so this can also be done for 3D materials like this gold or silver break junctions. In both cases, there's the rearrangement of few atoms, and chemical bonds are broken and formed under bias. So that's the kind of effect or forces that we are studying. Yeah, the motion of atoms due to this current-induced forces. And main contributions to these forces are the momentum transfer of electrons to the atoms, which in literature is often used to explain electromigration. And then there's phonon excitation interaction, often in literature referred to as Joule heating, and other phenomena due to the quantum nature of the electron. And as I just showed you, these forces can be exploited to shape structures or build switches, but on the negative side, they're actually one of the main limitation to the downscaling of nanoscale devices if the functionality should depend only on the position of few atoms, then these effects become relevant. So in my presentation, so that's an outline of my talk, I want to focus on 3 systems. The first is a graphene nanoribbon. That's a purely theoretical study. Then in the second part, I want to show an example where these forces can actually be measured in experiment using this C60 STM setup. And so these will be static examples, including only the adiabatic part of the force. While in the last part of my talk, I want to show a molecular dynamics simulation with current using this gold for this gold chain. Okay, so I'm using the Siesta software package, which is based on density functional theory and non-equilibrium Green's functions. Within this theory, the force on an atom is defined as the change of the Hamiltonian with respect to the atomic coordinate. To average, you take the trace over the force operator times the density matrix. And so we first relax the structures at 0 pi at equilibrium using Siesta, and then we attach electrodes, electron reservoirs to the structure, and apply a potential difference such that there's an electron flow across the system. And yeah, then you get here a bias dependence in the density matrix and in the Hamiltonian. And this is the adiabatic limit, or Born-Oppenheimer, because we're just calculating these forces and we're not really looking at the motion or back action of the atoms. Okay, so let me start with the graphene constriction here, a very small graphene constriction at 1 volt. We are symmetrically shifting the chemical potentials in the electrodes, and this leads to a potential drop here across the system, which induces charge rearrangement and forces on the atoms. And to simplify this picture, we project these forces onto the bonds. That's the definition. So we take the difference of the force onto atoms and project onto their connection onto the distance vector. Now we wanted to relate these forces. Yeah, so you see here blue you see repulsive forces, and in red you see compressive forces. And so we wanted to relate this force pattern to other quantities now in the system. And for this we have, for example, calculated bond currents, so the current through a bond. And this is a scatter plot, bond currents over these bond forces. And we couldn't find a very simple correlation, or at least no clear correlation. So we wanted to connect it to this charge picture, and to kind of simplify these induced charges here, we also project them onto the bonds. And just to explain here in a simple 2-orbital model that form a bond, this charge in the bond, that's kind of this term here. So that's this overlap term. So we also call this bond charge overlap population. And yeah, this term can actually be positive or negative. So so positive for a bonding and negative for an anti-bonding state. And by looking at the energy dependence of this term, you can actually analyze the bonding or bonding or anti-bonding character of the states, which in the literature is also called crystal orbital overlap population. Yeah, so a method to find out whether in a certain energy range states are bonding or anti-bonding. Okay, yeah, so we could actually find that these induced bond forces and the change in the overlap population, this is a scatter plot here, are correlated. When you get an increase in bond charge, so that's this, you see a bond strengthening force, or a decrease in bond charge is a bond weakening force. Yeah, and the idea to take bond charge as a measure of the bond strength was already suggested previously and studied also in other works. Okay, now let me get to the second part. This is the C60 terminated STM tip on top of a layer of C60 or of isolated, so islands of isolated C60s. These are experiments by Jörg Kröger at TU Ilmenau in Germany. So it's a combined AFM and STM setup, meaning they can pass a current and measure forces at the same time for different heights, so for different distances between the two C60s. And they get kind of these force parabolas. That's for the layer, that's for the isolated case. This is the curvature of the parabola. Yeah, and the force here for different distances, the colors are for different heights. The negative sign of the force here means that they get an attractive force. So, for example, for the isolated C60 contact, they get a high attractive force at negative bias. Yeah, and we have set up a model also of this junction and calculated bond forces using the method I just presented. Bond forces, so by summing over the contributions on the two C60s and calculate and projecting onto this the bond between the two C60s that is formed. And yeah, we can nicely reproduce the parabolas here in the case with also the higher attractive force at negative bias. And we also find the correlation to the change in the bond charge, so the bond between the two C60s. And in our paper, we have also, so this is our paper, we have also analyzed which are the orbitals relevant for bond formation in the conductance window. And we have actually shown that the applied bias leads to a filling of bonding states and depletion of anti-bonding states, which both causes this bond strengthening force where the effect is more pronounced at negative bias. That's why we see this higher attractive force at negative bias. And yeah, you're invited to read more in the paper on details of that. So in the last part of the talk, I'll present the results of the actual MD simulation that goes beyond the adiabatic limit. And so this is based on the semi-classical Langevin equation. This is the structure of a gold chain between gold contacts that we attach to electron and phonon path. And then we define a dynamical region for which phonon frequencies and electron-phonon couplings are calculated. For this, we use the Siesta and Inelastica tool. So Inelastica is for phonon, it's a tool for phonon calculations. And so with this, we calculate all parameters that enter the equation. Let me briefly explain the equation. So the force on an atom at coordinate x is equal to, this is like the harmonic force, so like a spring, plus this term that's the adiabatic force. And then you have these two contributions, this force term due to the current. And the first one here involves the phonon self-energy that we have calculated using Inelastica. And it represents a friction that the atoms feel due to the presence of the electron, so of the current in the system. And to account for the statistical nature of the electron movement, this is connected also to a term, to a random noise term of the force. So here, this term I said in the harmonic approximation, it's kind of, this is the dynamical matrix containing the spring constants of the system. But we can also run a full ab initio molecular dynamics simulation by replacing this term, so by the force calculated with Siesta. So yeah, this goes beyond the harmonic approximation, including anharmonic terms. Okay, So we have implemented this in IPy, and details about this equation or the implementation can be found in this works. Okay, so we run the simulation and we get a trajectory of the atoms driven by the current. And what quantities do we actually analyze? So and we look at the velocity correlation function, because integrated over energy or over frequency gives the kinetic energy of the system. So this is kind of, let me explain this figure. Here you have these blue lines that are the phono frequencies. And then the velocity correlation function has peaks at frequencies that are mainly excited by the current, and integrated, you see here, you have the energy, the kinetic energy. So that would kind of be the total kinetic energy in the system.
Sorry, Suzanne, you have 2 minutes left.
Okay,
Okay.
I'll be done. Okay, then, yeah, so going beyond the harmonic approximation means you include actually coupling between the modes. So in the harmonic case, you have decoupled modes, while in the harmonic, with the ab initio run, you induce coupling that leads to an energy redistribution. So that's kind of what you see here. In the harmonic case, you have this very excited mode, and in the ab initio case, the energy gets redistributed. So kind of that from the high frequency to the low frequency. So this kind of energy, it goes to the low frequencies. So this kind of shows that anharmonic effects actually play a role and should be treated also. Okay, so that's actually my last slide. Then to get a space-resolved representation, we have calculated the kinetic energy per bond, by defining a bond velocity. So that's what you can see here, a color plot of this bond kinetic energy, which kind of shows how much kinetic energy is in a bond. And you see that some of the bonds are have a specifically high kinetic energy, and the literature also referred to as hotspots in the junction. And this is the bond length distribution throughout the whole simulation. And you see that for this highly excited bonds, the bond length, so the bond distribution is much broader and at finite bias compared to zero bias, and so the bonds gets much more elongated throughout the run. And yeah, we hope to mainly to describe breaking processes in this way. So maybe the structure would at one point, at one bias, break at this point. Okay, so that brings me to the conclusion. I have shown you that bond forces and the change of bond population is correlated, and it has to do with filling and depletion of bonding and anti-bonding states. And then I have shown you the MD simulation that, yeah, anharmonic effects are important, and that there can be this bond, we can see this bond hotspot. Yeah, and with this, I would like to thank you for your attention.
Okay, thanks. Thanks a lot. Okay, so we have time for a couple of questions, so you can switch on your microphone or type in the chat.
So maybe can I ask a question?
Yeah, go ahead.
Okay, so did you so far already see any breaking processes, or did you not analyze them yet with this method?
No, we did not analyze them because so if we really want to simulate breaking processes, then with this kind of MD simulation, then we would maybe have to set some more boundary conditions, because if the structure really breaks, then the current goes to zero, and then also these force contributions would go to zero. And yeah, we have to think about how to do that. So we did not really look at breaking processes yet, yeah.
I see, okay. And in the first part, you just calculated these forces based, ignoring electronic friction and so on.
Yeah, exactly. It's just
a static picture.
Yeah, it's just a static picture. And so we could also relax the structures at finite bias, so we did that, but the relaxations were kind of small and did not really, yeah.
I see. I think these pictures of the bond forces are quite complex. Could we maybe go to the C60 example?
Yeah.
Okay, so at what, I was just wondering exactly in this picture, so on the left side, at what, where do I see the distance? So it's all between C60, C60 here.
Yeah.
I see. Okay, maybe I need to take a look at the picture, but let's say in this left picture and the C and D, what is the kind of interatomic distance there between the Cs?
So the interatomic distance in the experiments are not, they are not well defined. They cannot really measure this. They take a reference distance. But in the, yeah, so these are our distances kind of here.
But this would mean that, is that right? Am I wrong now? Or is this, okay, 1.4 angstroms, that would be below what I would think is a CC carbon distance. Is that right?
Yes.
So you squeeze them together or something?
No, yeah, the bond can be, it's not, it's smaller than the equilibrium distance.
I see.
Yeah, that's taking in reference to the equilibrium distance. Yeah, so you go below that. Yeah.
Okay, thanks.
You're welcome.
Okay, thanks. I think there is a question from Jean-Yves.
Yes, hello. Thank you for the very nice presentation. You somehow give a reply already, but I was wondering for the first part with the graphene nanoribbon.
Yeah.
So you obviously have a pattern in your forces. So did you try to relax it, and how big are the changes? And at the end, what are the properties of the nanoribbon when you follow those forces?
Yeah, so we try to do that. We try to relax also the structures. That means that the forces are zero then, so we cannot study forces anymore. But yeah, the relaxations were small. They were a little bit too small to really see big changes in the geometry. So that's why we have focused here on the forces and try to understand the forces.
Okay, fair enough. Thank you.
Okay, thanks a lot. If there are no more questions, we can thank again the speaker. We can clap the hands. Okay, thanks a lot. We move to the next speaker, who is Giuseppe Celardo.
Okay, here I am. So
okay.
Let me share. No, I need to share my screen, right?
In the darkness, yes. You.
No, I'm not enabled to share my screen, so somebody should enable.
You're not co-host, so
I'll do it in a second.
Mariela, yeah, you should co-host.
Sorry, that good.
No.
Yeah, now you should be able.
Okay, now you should be able.
Yes, just a second. Okay. Okay, so let me go to full screen. Okay, so thank you very much to the organizer of this workshop, in particular to Claudio and Mariella. So I noticed that most of the audience is experimentalist, so I will try to, I'm a poor theorist, but I will try to stay simple. So what the main message of this talk on the following talk by Francesco Mattiotti is that we want to use long-range interaction to achieve efficient transport. Okay, now we are going to talk about long-range interaction, what is cooperative shielding, and how it is related to localization and transport. So of course, achieving ultra-efficient transport is a fundamental issue in many quantum technologies applications. And to do this, we need to understand the role of disorder. Of course, the Anderson theory of localization is a beacon to guide us through disordered system and how disorder will affect transport properties. Nevertheless, Anderson localization works under specific conditions where the particle can hope only a short distances, okay, only nearest neighbor hoping, for instance. The disorder should be uncorrelated, disorder between, I don't know, the site energy where the particle can jump, and the system should be closed. So here in this talk, I will give you an overview of what is known when one of these conditions, in particular, instead of short range hopping, we have long range. And long range occurs in many realistic systems like cold atomic clouds, in ion traps. It has been emulated in these years. We will see, Francesco basically will show you that emitters in resonant cavities also, due to the coupling mediated by the cavity, the cavity mode can have a long range interaction. So, so fundamentally, it's important to understand the long range is not only does not only arise due to microscopic interaction, but it can also be mediated to the decoupling between a system and another system, external system. So the main concepts I will introduce in this talk is about cooperative shielding and localization. We will see what is this about. Okay, if I have time, I will mention the two topics about open system and many-body system, but I don't think there is enough time. So first of all, about localization and long range, let's say the common law, the general idea, dates back to Anderson and then to Levitov in the 90s, is that long range should destroy localization. The idea on this is that since you have the possibility, a single particle possibility to reach very far away sites, and if there is disorder, you will always find a site which is at resonance, and so the particle can move freely, and the localization effect, which is an effect that induces the particle to stay put, not to spread, not to diffuse due to disorder, so should be broken. And these ideas, this general expectation has been confirmed by several studies. For instance, Mirlin and Fyodorov are part of Levitov that I mentioned. On the other hand, recently, also the opposite has been found. For instance, there is this nice work called Osipov in 2013, where it shows that if you have a very long range interaction, actually interaction that don't decay with the distance, you have strong signature of localization. And then we published a paper in which we explain this contradiction, proposing this cooperative shielding effect. This is what I'm gonna talk now, okay? But before talking about the shielding, there is another issue I want to address. So the key difference between the previous work and the late work about the relation between long range and localization is that in the previous work, they considered uncorrelated long range interactions, so meaning that the hopping could be random from one particle. So let's say this particle can jump to these sites, and this hopping amplitude are randomly distributed. On the other side, when you have, and in this case it's true, when the hopping is uncorrelated, that you destroy localization. On the other hand, when the hopping is correlated, then we will see we have cooperative shielding and signature of localization can be preserved. So and to make you understand the difference between correlated long range and uncorrelated long range, let's take like a simple model. We consider like a bunch of sites, here two for instance, connected by an hopping coupling. Here it doesn't matter if it is correlated or uncorrelated because there is only one coupling. And of course, this is the survival probability. So the probability if you start from site one to stay in site one. And of course, you will oscillate because of this resonant coupling between 0 and 1. Now, as we increase the number of sites, here, for instance, for 40 sites, we have one particle can jump to all the other sites, either with a correlated hopping or with an uncorrelated hopping. And the differences are striking. For a correlated hopping, so if the hopping amplitude is all the same, basically the particle doesn't go anywhere. It stays put where it starts, which is counterintuitive because you can go anywhere with the same amplitude. And so you would expect to spread very fast around. And this is what happens actually. This is the red curve for uncorrelated disorder. Okay, as you see, the reason why the particle doesn't go away, even if it is connected to all the sites, is this cooperative shielding effect that I will mention now. So the idea of this cooperative shielding is that the dynamical evolution in a long-range interacting system, where the interaction is correlated, can be effectively described by a short-range Hamiltonian. And in particular, if the range of the interaction is independent of the distance, then the dynamics, then you can simply eliminate the long-range interaction from your dynamics, and the dynamics without long-range interaction is identical to the dynamics with long-range interaction up to a time scale which diverges with the system size. So to show these, we studied several systems, but this is just a 1D chain Anderson model. So there is a nearest neighbor opening and there is disorder. On the top of it, there is also this long-range distant independence, for instance, disorder. And here is an example of what, let me try to move this, don't know how to move this bar away. Okay, let's see. So, and this is an example of what shielding implies, you see. Say that I start with an excitation in the middle of the chain, is an antisymmetric superposition of two sites in the middle of this chain. Then I make them evolve for a very long time. And the black curve represents the evolution with a full Hamiltonian, meaning that, you know, the Anderson model plus the long range hopping, right? Like, while the red dashed line represents evolution only with the Anderson model. So where long range has been eliminated. And this is the probability distribution on the chain for 20 sites and for 200 sites. As you see, as I increase the number of sites, because this is a cooperative effect. So remember, as you increase n, these shielding effects become stronger. As I increase n, basically the two evolution becomes very close one to another. And these are very, very different Hamiltonian. One has long range, one doesn't have long range. So we completely eliminated long range. And this is shows what shielding, what cooperative shielding means. And now, to understand better why shielding arises, I mean, there are many issues, but here I just want to focus on one thing. So let's take this Hamiltonian that I'm considering. So there is this nearest neighbor coupling, there is this all-to-all, distant independent hopping, and then there is disorder, right? Now, the nearest neighbor coupling and the long range, they commute with each other. The long range will introduce a gap, an energy gap between the ground state and the excited states, and this is typical of long range. Another typical thing of long range is that the subspaces, the eigensubspaces are highly degenerate. And indeed, in this specific case, if I take a distant independent coupling, but this is the same effect would occur in the different features, but also with a finite long range. So a long range that decays, the interaction that decays with distance. And anyway, in this case, all these states are degenerate. So they belong to an eigensubspace of V. So you understand, if I start here, V will give me just a global phase. So the dynamics will be only determined by this term, because these are degenerate subspaces of V. And since it's gapped, the other only, let's say, different eigenvalue corresponds to this ground state, which is gapped. And since it's gapped, let's say, even if I add disorder, it will be hard to be mixed, right, with these other states. So this shielding effect will survive in presence of disorder until, let's say, there is a gap. And the gap equation here in long-range system is the same of the Cooper model in superconductivity, basically, is this equation. This is another interesting features of correlated long-range system. They induce a gap, which is formally equivalent to the Cooper model gap. And this connection has been done in this paper by our group. Okay, finally, I would like to mention so in the gapped regime, again, the presence of a gap is typical long range. We have the ground state is extended, but the excited states are peculiar. Since in this space, let's say the long range is suppressed, then the common idea that long range should suppress localization is not true anymore, because long range is suppressed, so localization can emerge again. This is somehow true. Indeed, the eigenfunction in of these excited states have an exponentially localized peak, but there is also, let's say, a feature that reminds us that long range is always there. So there is this extended tail of this eigenfunction. So this is the probability distribution of the average eigenfunction in the excited states. These are hybrid because they are exponentially localized, but at the same time, they have an extended tail. The most interesting features of these excited states is that these states can be completely independent of disorder. Here I show 3 values of disorder which span an order of magnitude, and you see that the probability, the amplitude of these states is independent of disorder. And these, as Francesco will show, will allow us to exploit these hybrid states that even if they show features of localization, due to this robust tail, which do not depend on disorder, they can actually lead to a transport which is independent of disorder, which is quite non-trivial. And okay, I don't want to enter in other things. This is a work we did on open system, and this is a work we did about cooperative shielding in many body system. Our theoretical prediction has been confirmed by an experiment of the Monroe group in Maryland, where even in a many body system, this cooperative shielding effect can be seen. So long range is suppressed, and you can have a frozen evolution or an evolution.
Lucas, sorry, you have 3 minutes left.
Okay. Or an evolution which is as if there is a short range Hamiltonian governing the dynamics of the system, and not a long range Hamiltonian. Okay, since I have 3 minutes left, I just want to mention very briefly that we also studied an open system, okay, when there is a long range, but this is a cold atomic clouds. You excite it with a laser. This is in collaboration with Robin Kaiser in Nice, and then you want to localize light, right, in these cold atomic clouds. And yeah, there is long range, and there is also opening, because you know, the excitation which is absorbed by the cloud can be lost, can be re-emitted. And now this cooperative shielding effect can induce the possibility to observe localized states in this system. And actually there is an emergence of a delocalized, localized phase transition, which depends, so we call it mobility edge in the imaginary axis, because it depends on the lifetime of the states and not on their energy. And usually mobility edge or metal insulator transitions depends on the energy. So I conclude, okay, just saying again, long-range interaction system are very peculiar, very interesting they show very interesting properties with respect to how they react to disorder, and the possibility to exploit these properties to have robust transport will be discussed by Francesco in the next talk. I am done. Hopefully in time. Yes, I think so.
Yeah, in perfect time. Thanks a lot, Luca. So we can clap the hands. Okay, so now it is exactly, unfortunately. So it's open for questions. I start, sorry, Luca, with a very general one from a poor experimentalist. So what is the difference between this cooperative shielding and what usually people call the many-body localization, which is, I mean, localization with disorder in an interacting system?
Yes, no, it's a fair question. There are 2 different topics in reality. I mean, many-body localization is when usually the people study when you have short range and you put disorder, but instead of just one excitation in your system, no, you have many excitation, and so you have many body, okay? And this is many-body localization is the idea how you want to generalize what happens in a single excitation when there is disorder, Anderson localization, etc. You want to understand how many-body interaction, right, would change the picture. Here, the shielding is about, even if there is no disorder, the shielding is an effect for which, if you start in subspaces, then the evolution occurs as if long range either is not there or is effectively suppressed and becomes an effective short range interaction. So is an effect in which the short range is reduced from the dynamics, is eliminated or suppressed and reduced to a short range evolution. And so, these, yeah,
yes.
Sorry.
No, yeah, but I mean, the final result is similar. You can have localization. So I'm wondering whether you're including the long range in your case is a way of mimicking what happens if you have the many body correlations.
No, I mean, this many body localization.
In the final result is more or less
let's
similar.
Let's say, is the point of view, is the final results, you know, the final result, it depends on what are the interaction there. But anyway, this effect focus on the interaction, you see what I mean? While many body localization focus on the interplay of interaction with disorder. So, and actually it's an open question. Yours is a good question. What are the relations? So what happens to the phenomenon of many body localization in presence of long range when the long range is correlated and we know there is the shielding effect, okay? This is a question that has not been answered yet. So this is a good question, but there is no, it has to be studied yet. You see what I mean?
Yeah,
they're not the same thing, they're not the same thing. So many body localization and shielding is different, are different stories. They have an interplay, you're right, but what is the precise interplay is not known. Huh?
Not clear. Okay, many thanks. Very interesting. Okay, so if there is any other question, you can switch on your microphone.
I hope I didn't scare anybody off for the next talk.
You put some hype on the next talk, so.
Yeah. Some high expectation.
Exactly. Okay, I think we can thank Luca again. Thank you a lot.
Thank you.
We clap again the hands. Okay. Thanks a lot, Luca. We move to the last talk of this session, but also of this symposium. So Francesco Mattiotti, you can okay, you can switch on the microphone. Okay, you can also share the presentation.
All right. Okay. Thank you. Okay. Thank you very much, Claudio, and thank you all the organizers for this very interesting gathering. Today, what I'm going to talk about is a work made in collaboration with Luca that just introduced very well the general topic, and our collaborators in Puebla, and is about transport in one-dimensional systems in presence of long-range hopping. As we see, long-range hopping can have a very useful effect on transport. So basically, I'm just summarizing some of the main points of Luca's introduction. So disorder in a short-range interacting system has the effect of localizing the excitation. So while for a clean linear chain, you would have a spreading of excitation as in the above here. The presence of disorder would confine an excitation initially placed on a disordered system to stay there in the very exponentially close to the initial site. And the effect of this on transport is to exponentially suppress basically the transmission coefficient. On the other hand, the localization, long-range interaction are typically connected to the localization, but specifically correlated long-range interaction, so an equal hopping between the sites leads to the emergence of a gap within the excitonic spectrum of the system. And to this gap, one can associate a critical disorder. So the interplay of disorder on a long-range interacting system is that of, as long as disorder is smaller of the gap, basically this order acts only on the subspace of the non-gapped state, which here are the excited states, while at some point when this order is large enough, then the gap is filled and long-range effects are destroyed. But in this gapped regime, the features of these excited states, which form the vast majority of the spectrum, are in a sense hybrid between the localized states that you would have in a short-range disorder chain, with also some long-range feature, which is a plateau, so a constant probability to find the excitation everywhere in the system. So the general question is how do these particular hybrid states with their hybrid strange structure affect transport, and what's the effect of long range on transport in this situation? So we address this question by studying 1D Anderson model, so disorder energy levels with the nearest neighbor hopping, with the addition of a long-range correlated all-to-all interaction, as described above. And we study transport by including pumping of excitation on the first site and on one edge of the chain, let's say, and draining of excitation from the opposite edge. Pumping and draining are described through a Lindblad master equation, so they are incoherent pumping and draining processes, and then one can study the current transmitted through the system. I want also to point out to a more physical system, in a sense, which is still an Anderson chain with disorder energy levels, but where every site of the chain is coupled to the same mode of a Fabry-Perot cavity. This system, which has a different Hamiltonian, can, as long as the coupling to the cavity is large enough, this system can be mapped analytically to a long-range interacting system, and as I will show in a few slides, this leads to basically identical transport features between a long-range and cavity system. So as a figure of merit of transport, we study the steady-state current transmitted through the system in the presence of pumping and draining. So one just solves the master equation at the steady state, and one can compute the current like this. But the problem from the practical point of view is that it's computationally expensive, but one is limited by chains of just few hundreds of elements. So it's limiting also to compare to the experiments. So we explored other figures of merit. In particular, I want to introduce here the average escape time from the chain. So by this, I mean we consider a chain without pumping. We initialize the excitation on the, say, pumping site, and then we let the system evolve in presence of the non-Hermitian Hamiltonian, which is just the bare Hamiltonian of the chain with disorder, long range, etc., plus a non-Hermitian term which mimics, which models the loss of excitation from the opposite side of the chain. So this time really measures how long it takes an excitation initially placed on one edge of the chain to be drained out through the opposite side of the chain. And it measures effectively the depletion time of the chain upon excitation. So we use this parameter, which is easier to compute than the current, because it just requires to deal with an Hamiltonian. We place this parameter in an effective rate equation And from this, we can have an equivalent, an alternative definition of the steady state current. Interestingly, even if this approach is quite different from solving the master equation, through all the parameter range that we analyze, changing the pumping rate, the draining rate, disorder, and the long-range interaction, we found that these two definitions of current give the exact same results. So we just stick with the second one for convenience, because it allows to study really long chains. So now I'm going to present our results. And at first, I'm going to show some results about the chain with the long range all-to-all interaction. Here in this figure, I'm plotting the steady state current as a function of disorder. Remember, okay, now I want to make you notice that all the region of disorder of parameters here to the left of this red dashed line is the gapped regime. So where disorder is smaller than the gap induced by the long range interaction. And so now the feature of the dependence of current on disorder, at first, at very small disorder, is the same of the simple standard Anderson chain. So initially current decreases with disorder as it would do if it wouldn't have a long-range interaction. But then a critical point is reached here, which we label W1, where the dependence of current on disorder changes, and for more than an order of magnitudes in the disorder parameter here, the current increases with disorder. We call this regime DET, which is disorder enhanced transport. And it's quite a counterintuitive effect, because, of course, one thinks that in general disorder would keep on quenching transport in a continuous way. So then this disorder enhanced regime extends up to a second critical point, which we label W2. We can estimate both value on a study of the eigenfunction, as I will say later. So beyond this second critical value, W2, the dependence of current becomes independent of disorder. So we have first a disorder enhanced transport regime, and after that a DIT, so disorder independent transport regime. And this second regime extends from this W2 critical value up to the third critical disorder W gap, which is the point where disorder is so large that it fills the gap and it destroys the long range effects. And beyond the W gap, then the current recovers its typical behavior of decreasing with disorder. So as we see here, the effect of long range is to enhance largely the current in presence of disorder of a very wide range with respect to the coupling. And since this property is shared by different figures of merit of transport, we basically connect this feature to the characteristic of the hybrid eigenfunctions of the excited states of the system. So in the disorder enhanced transport regime, the eigenfunctions have this hybrid structure with a peak and a plateau. But as you can see, as you increase disorder in this yellow region, what happens is that the peak shrinks while the extended plateau, which is the byproduct of the long-range interaction, increases with disorder. And since it's the plateau that sustains transport, this is what produces the disorder-enhanced transport in this region. On the other end, in the disorder-independent regime, the eigenfunctions are independent of the value of disorder. So they all look the same, like in this panel below here. There is a peak localized on one side, and then a constant plateau through all the other sides. And as you can see, varying W by an order of magnitude doesn't change the picture at all. So,
Just 2 minutes left.
Okay, thank you. So here as we can see, we are able to map the long-range model to the cavity model under the condition that we are in the gapped regime, and we can analytically find a mapping relation between the all-to-all gamma parameter and the G coupling of these atoms through a common cavity mode in a cavity. What we show here is that with a model of an Anderson chain where all the atoms are coupled to the same cavity mode, if we measure the current versus disorder, we see the same features, even choosing parameters which are reasonable compared to recent experiments. And here the dashed line is a reasonable typical range of values of disorder. So this disorder-enhanced regime is seems likely to be it's possible to be observed from these estimates. So our intuition is the following. At first, for small disorder, localization is playing the major role, destroying transport, but then at the same time, disorder also mixes the hybrid eigenfunction with the gapped state, basically giving the localization property to the localized excited states of the system. So at some point, a crossover is reached that we are able to estimate, and beyond this crossover, which is W1, we have the disorder-enhanced transport where on increasing disorder, the mixing between localized states and the gap state increases, and so the transport properties of the system increase. Then a maximal mixing is reached at some point when the localization length becomes equal to the lattice step in the chain, and then ultimately for the large disorder, the gap is closed, and then localization kicks in again, destroying the transport. So this is our intuition behind what we have seen, and as a conclusion, then we have shown that long-range hopping can lead to disorder-enhanced transport and also disorder-independent transport regimes. These regimes extend over several orders of magnitudes of the disorder strength. And then we also seen that a linear molecular chain, a disorder chain in an optical cavity with a resonant cavity mode, which is a realistic model in a sense, is actually equivalent to have a long-range hopping through the sides of the chain. So in perspective, the main missing part from our model is the effect of the coherence and finite temperature. So we are planning to include dephasing. Specifically, we're interested to see what happens with the finite temperature dephasing and see how these regimes that we just found would behave in presence of thermal noise. And with this, I finished, and thank you very much for your attention.
Thank you, Francesco. So we clap the hands. Okay. So now it's open for questions. So we can ask Francesco what we want. David, go ahead.
I was just wondering, how does the current depend on gamma, on the amplitude of the hopping, and also how does it depend on n, the size of the chain?
Okay, thank you very much for the question. I have an additional slide here. Okay, here I'm mixing a bit between the long-range model and the cavity model, but as I've seen, they are equivalent. So if you change the length of the chain, the current, so for very small w, the current goes as 1 over n in the ballistic regime, while in this disorder-independent transport regime, the current goes as 1 over n square. N is the number of sites in the chain. And the critical disorder W1 here decreases and goes to 0 when you increase the length of the chain. So the regime survives. Then the effect of the long-range coupling is just visible on the last, on the highest critical disorder here. So if you increase the strength of the long-range coupling, you're just increasing the critical disorder where the gap is destroyed. But anything that happens below the W gap is independent of the strength of the longer range coupling. So this is the main scaling. Does it answer your question?
Okay, yeah. So basically, for small disorder, it doesn't depend on either the coupling strength or the amplitude of this long-range hopping.
Yeah. So if W is if disorder is less than the gap, yes, it's like having an infinite gap in a sense.
Okay, thank you.
Yes.
Okay. Francesco, just a curiosity. I mean, this W gap, so the regime with the largest disorder, is it physically achievable? Because I mean, this happens for very, very large disorder. If you go back, it was 10,000 the hopping, something like that. If you go back.
So okay.
So is there any physical system in which you can really achieve this regime?
Yeah. So we have an example for molecular chains, for example, where this detailed parameter. So if you have a nearest neighbor coupling of the order of room temperature, a chain, a molecular chain of 100,000 molecules, if I mean, you would need a Rabi splitting given, for example, by resonant cavity of the order of 1 eV, but this can be done under some choice of the material. And with this parameter for a molecular chain, you can really have a W gap which is huge, of the order of 10 eV, so that the realistic range of disorder would fall basically within the disorder enhanced region. So yes, it is possible. Of course, you would need a large gap, but if you have a strong coupling to the cavity, this is possible. Also, read bare atoms, polar molecules, or ion traps can have a strong coupling to a cavity mode or an effective long-range coupling, which could be large enough to see these regimes. So these are our candidates, let's say, to see this effect in the real life. But yeah.
And here, sorry, in this model, you inject excitation in one side and you collect on the other side. Exactly.
But, so
yeah. Okay, but in principle, can you use a similar model to describe, for example, photo excitation? So you create excitations with light, so you increase the number of excitation, and then you collect them through some.
Okay, yes, it's very easy to include excitation from a coherent laser. So you would just add the light matter Hamiltonian to the bare Hamiltonian here. And yes, you can tune your model to choose how many sites are excited, where, with which frequency and which intensity. So that's an easy way to extend the model and to apply it to more realistic situations. Yes. You can also include the thermal light quite easily, just replacing the pumping operator, basically.
Yeah. Okay, many thanks.
Thank you.
So let's see, there are other questions. Okay, I think we can thank Francesco. Okay, thank you for this last talk. I think we are at the end of the, not only of the session, but also of the symposium. So we can ask everybody to switch on the camera and take a picture. Mariela, is it correct?
Yes, let's do that
okay,
today as well.
Okay, so if you can switch on the camera, we
have, oh, sorry.
We take a picture, okay?
Okay, smile.
Okay.
All right.
Okay, and we thank you all for the participation. So we tried, as you saw, we tried to bring together different fields, because I mean this field of emerging properties in emergent transport properties, I mean, mixes together many different fields from quantum transport to superconductivity. So we try to merge different fields. We hope that you enjoyed and you took some inspiration from talks, even from other fields.
Yeah.
Thank you. Bye bye to everybody.
Thanks everyone. And yeah, we hope that you enjoy. There is still one last plenary session this afternoon of the conference, so you are all welcome to join, and also the closing session. And I think we can say we hope to see you next time in real life. I think this has been a very interesting experience, and I guess new for everyone. I want to say, I also thank Luca in this case. I don't think, Francesco, you are here in Europe, but Luca is in Mexico. And we had previously also another speaker.
Now it's 5:30 in the morning.
Yes, so that's very brave what you have done. Thanks a lot, and have a nice day.
Thank you, Mariella.
Yeah,
thank you,
nice
Claudio. Thank you, everybody.
Yeah.
Thanks, bye.
Thank you.
Thank you.